A supersized bridge built in an active earthquake zone.
As we stand here, it can happen at any moment.
It's cutting-edge structural engineering.
A big part of the construction, it's underwater.
And the pioneering historic designs.
All 100 men were hanging on as the fort was sinking at 35 degrees.
You can see each wire is actually breaking one after another.
That made the impossible possible.
And what you see, something that is unique.
In August 2004, the Rion-Antirion Bridge opened to traffic for the first time. The mighty structure is an engineering masterpiece of the modern age. Spanning almost 3 kilometers across the Gulf of Corinth, this engineering colossus boasts the longest fully suspended deck, the deepest foundations, and the largest supporting piers of any bridge on Earth. For Chief Engineer Panagiotis Papanikolas, it was a project he had dreamt of for years.
The bridge was something that always excited me, that one day maybe it will happen.
However, a catalogue of natural challenges meant that, for centuries, the idea of bridging this foreboding water had seemed impossible.
We are sitting now from the side of the Peloponnese, and across is the continental Greece. Years ago, those things were very close, and then they start drifted apart. There is tectonic faults all along this area, and we are bound by mountains from both sides. And the geometry of these sections makes it a natural wind tunnel.
And there was another earth-shattering challenge.
This particular strait here is the highest seismic zone of Greece and the highest seismic zone of Europe.
It's a long list of seemingly insurmountable engineering problems. The two landmasses either side are constantly drifting apart. There's deep water, high winds, and major earthquake risks. All of which combine to make the building of the Rion-Antirion Bridge a huge, apparently unachievable undertaking. But the need for a safe crossing was desperate. The perilous waters of the Gulf of Corinth often made ferry crossings impossible and cut the peninsula off from important services.
There are examples of people that lost their lives because the ferries were not crossing due to bad weather and they could not come to the hospital. There was a need of this bridge.
So, in the 1990s, the government decided to attempt one of the most ambitious engineering feats in modern Greek history. The first seemingly impossible challenge to overcome was the almost 3-kilometer gap between the two shorelines. The vast expanse meant a single-span bridge was out of the question. So any design would require building supporting towers into waters up to 65 meters deep, far deeper than any bridge designer would willingly choose.
The cross-sections below sea level, we go to deep waters from very beginning of the shore. No matter what type of bridge we want to select, we could not escape the depth of water.
In order to overcome this daunting obstacle, Panagiotis and his fellow engineers would need to draw on history's great innovators to make the impossible possible. Building in water has always taxed engineers to the limit. Early lighthouses relied on Mother Nature to provide convenient rock for foundations. Fine for lighthouses, useless for bridge building. Creating artificial islands was time-consuming and impractical in deep water. In the 19th century, pressurized structures called caissons were developed to create underwater building sites, but they were both difficult and dangerous. Fortunately, in the 20th century, a new technique was on the horizon. To build a bridge across the mighty Gulf of Corinth, engineers would need to draw on a radical technique, brilliantly exploited by a bold British engineer nearly 6 decades earlier. Engineering genius Guy Maunsell would develop a method in the 1940s that emphatically conquered the challenge of building at sea. Professor Luke Bisbee is heading out far into the English Channel to see the remains of one of the engineering innovator's most audacious and seemingly impossible creations.
Maunsell's influence in contemporary engineering, I don't think, really can be overstated. This was really the first time that this had ever been attempted, and so it was really quite a daring feat of engineering.
It was an innovation triggered by the Second World War. At the outbreak of the war, it became clear that the River Thames was a prime target for German bombers, wanting to destroy London's docks and lay mines to disrupt Allied shipping. So civil engineer Guy Maunsell suggested a radical new design for offshore sea defences. Naval forts consisting of 2 80-foot-high concrete towers, each containing 4 floors of accommodation and topped by a gun deck. However, the ingenious part of Maunsell's design was not the layout of the fort, but how they would be constructed and deployed. These forts, like one known as Knock John that Luke is visiting, completely broke the mold.
Knock John here was towed out 3 to 6 miles from where it was constructed on land, and then it was sunk in place, out exactly where you see it.
Maunsell's brilliant idea was to design the bases of the forts as huge hollow concrete barges that, despite their enormous weight, had the buoyancy to float.
Maunsell built the forts on top of these large concrete barges and then calculated how large the barges needed to be in order to hold the weight of the fort so they could be taken out and then sunk in place.
After being constructed in a dry dock, the massive 4,500-ton concrete forts were towed far out to sea, complete with its 100-man crew already on board.
When they had it in the place where they wanted it, they essentially just pulled out a stopcock at one end and let the water flow in. As the water was flowing in, the barge started to list in the water, and eventually the nose dipped under the water.
Footage from the time shows just how dramatic and seemingly perilous the process was.
All 100 men were hanging on as the fort was sinking at 35 degrees.
Despite its terrifyingly dramatic submersion, Maunsell's groundbreaking design worked perfectly.
The bottom of the barge basically filled up with water, and eventually the entire barge sunk to the bottom and flattened out.
In the years ahead, the forts helped British forces shoot down 22 enemy aircraft and 30 flying bombs, not only protecting London from attack, but making engineering history at the same time.
The influence of this type of construction you can see in all different facets of engineering today. You can see it in the offshore oil and gas industry with oil platforms. You can see it being used as foundations for wind turbines. And of course, you can see it being used as a way of placing foundations for large bridge structures around the world.
And the most impressive use of floating concrete is at the Rion-Antirion Bridge. Facing the challenge of building 4 enormous concrete bridge supports, Papa Nicholas and his colleagues take the principles so brilliantly exploited by Guy Maunsell and supersize them. In 1998, construction begins. Each hollow pier footing is built in dry dock, but on a scale that Guy Maunsell could never have imagined. Each one is the size of a football field and weighs an extraordinary 70,000 tons. But before the footings can be moved into position, the engineers face an additional challenge that Maunsell didn't have. The Gulf of Corinth lies in one of the most active seismic zones in Europe. In an earthquake, the soft seabed there would liquefy, causing the piers to sink and the bridge to collapse. Unless an answer could be found, the project was destined to fail.
We had to find the solutions how to reinforce the subsoil in order to be able to handle those weights, those big structures, and also to withstand the earthquake.
The engineers come up with a radical solution. They drive hundreds of 30-meter-long tubes deep into the soil in the areas where the 4 piers are to sit.
Imagine the foundation being like a yogurt. It's like having yogurt, and you put stores inside to reinforce them.
This ingenious idea stabilizes the seabed. And where the bridge footings are usually anchored into the ground, here they are placed on a 3-meter-thick layer of gravel, allowing them to move freely in the event of an earthquake.
Very innovative design, first time done in engineering, first time done in this bridge. Without this solution, it would have been impossible to build the bridge.
With the foundations laid, the engineers maneuver the enormous concrete pier bases 1 kilometer out into the Gulf. The engineers then begin one of the most extraordinary and audacious parts of the build. They continue to build up the massive piers while they are still floating.
We are exactly in the area here where this portion that I'm sitting on is the one that was constructed in the dry dock and wet dock. And from here and further up, it was constructed in situ, right here at this location.
Each new layer of heavy concrete sinks the pier further, pushing it down towards the seabed. As building continues, the mega structure finally starts to rise from the waves. The end result is 4 enormous hollow foundation piers, unlike for any previous bridge, creating massive sub-aqua concrete caverns.
We are 64 meters below sea level. This is the footing. The footing has dimensions of around 90 meters in diameter. Just imagine a soccer field.
But in creating this cutting-edge modern wonder, its builders still face major challenges and will have to draw on innovations from the past.
So we are seeing this cascading failure right now due to, in this case, for example, a fire on the bridge.
To produce more impossible engineering. The Rion-Antirion Bridge crossing the Gulf of Corinth in Greece is a modern engineering marvel. 320,000 cubic meters of concrete, more than 100,000 tons of steel, and 62 kilometers of cabling have gone into creating the longest, fully suspended, cable-stayed bridge on the planet. In attempting a construction of this scale and complexity, Panagiotis Papanikolaou and his fellow engineers had set themselves a seemingly impossible challenge. The Gulf of Corinth is one of the most important and busiest shipping routes in Europe. Even at its narrowest, it's nearly 3 kilometers wide.
Of course, what you try to do is to find the closest possible part of the strait, so to have the smallest possible bridge for economical reasons. But of course, we had to respect the navigation channels.
To find a design capable of spanning this gap without interfering with shipping, the engineers need to turn to the great innovators of the past for inspiration. It was the Romans who first engineered solid bridges that were built to last, using stone and a simple revolutionary shape, the arch. However, the wider the gap, the more arches were needed, and the heavier the bridge became. For hundreds of years, Inca communities in the high Andes crossed gorges using suspended wooden walkways. It's said the 16th century Spanish conquistadors arriving in Peru looked in amazement and fear at the swaying bridges that might break at any moment. What was needed were new building materials and a new approach. And in 1826, one brilliant engineer showed how to do it in style. The Menai Suspension Bridge is arguably the ultimate achievement of Thomas Telford, one of Britain's finest ever civil engineers.
Telford was an accomplished engineer, of course. At this stage, he had designed canals and roads and bridges. He'd never built anything on this scale before, and so this bridge was to be really his greatest challenge.
The then busy Menai Strait separated mainland Wales from the island of Anglesey. Until then, bridging it would have been impossible. A traditional arch design would not only need to be enormous, but it would seriously impair the passage of tall ships along the waterway.
Imagine this as being the strait here, and these are the valley walls on either side of the strait. Basically, you cut your bits into shape, and you then have to gradually build your arch, adding the bits of the arch as you go. And if you imagine that as now being the completed arch, and we have our load coming along here, you can see that the compression forces that come from that car flow down through the various sections of the arch and into the abutments on either side of the valley. Now, the problem that Telford faced was that as you're building an arch, you would have to have some supports down here underneath the middle of the arch so that as you're building it, the blocks don't fall into the strait. And that would require some scaffolding. And this was just not acceptable to the Admiralty at the time because this is a very busy shipping channel and they required 100 feet of clearance above the high water mark. And that led Telford to have to consider something that could give him a very long, clear span with no supports in the water, even during construction.
What Telford came up with was the world's first major long-span suspension bridge.
For a suspension bridge, you need two very strong abutments, and then you need two towers. And then what you do is once you've built your towers, you take a cable like these guys, and you string these up and over the towers, and then you drop hanger cables down from the main cables, and then put your bridge deck in place. And then once your bridge is completed, if you have a load that comes along, say our car here, it comes along, and now when the load gets out near the middle of the span, the load from the car then gets transferred up through the hanger cables into the main cable up over the tower. The tension in that cable gets anchored in these strong abutments, and the compression force here goes down into the foundations in the bedrock. That's essentially how a suspension bridge works, like this beautiful bridge we have here.
Telford's suspended deck was a stroke of engineering virtuosity.
The key advantages of a suspension bridge are that you can span long distances with no supports below the bridge deck. So you can get very long, clear, unsupported spans because all of the support is coming from the suspending cables and the main cables up above you. So below the bridge deck, there's absolutely no obstructions, which in a strait is obviously a very important thing.
Clearly, a suspended bridge was the obvious solution for Papa Nicholas and his fellow engineers in the Gulf of Corinth. But they would have to do it on a whole other scale. When completed, the Rion-Antirion Bridge would need to be an incredible 7 times longer than the Menai. Unlike the main anchored cables of Telford's suspension bridge, this cable-stayed design uses individual cables, radiating from 4 huge pylons, spaced just half a kilometre apart. Each cable set holding up a 12-metre-long section of deck. In 2003, the mammoth operation of fitting the deck begins. The sections are floated out into the Gulf of Corinth and attached either side of each pylon until they meet in the middle, an operation that takes more than a year. But this bridge's engineers face another potentially deadly challenge that Thomas Telford didn't have to worry about in Menai. This is one of the most active earthquake zones in Europe.
The wind, it's a phenomenon which is predictable. So you are ready for it. You have designed the bridge to take it. Earthquake is something different.
Expansion joints allow the deck to stretch as the 2 land masses either side gradually drift apart. But protecting it against a massive earthquake will require a groundbreaking new approach.
What you see is a deck just going through the pylons, does not touch, does not sit on the pylons. This one has this unique feature of the full suspension deck.
Instead of resting on each pier, the deck hangs just above, creating one huge 2.3-kilometer long, fully suspended floating deck. If any earthquake strikes, flexibility is key. The piers can move on their foundations, and if the deck was attached when this happened, it could buckle and break. But it's also important that the deck doesn't sway during the regular high winds experienced in the Gulf. The problem the engineers face is how to ensure rigidity in normal conditions, but allow flexibility during earthquakes. The solution? The world's biggest shock absorbers.
They are similar with the shock absorbers that we have in the cars. They allow some movement, but what they do mostly, they absorb this energy.
If severe movement occurs, a simple fuse breaks and brings the massive dampers into play.
The moment that the fuse breaks, the small tube can get inside the large tube. At that point, the dampers come into action. This device does not work for years. And then one day, you want it to work, and everything has to be perfect. So if it was something too sophisticated, usually the moment you want them to work, they don't work.
This quake-busting design proved its worth 4 years after the bridge opened. When a 6.4 scale earthquake hit the Rion-Antirion in 2008, the innovative damping system kicked into action, saving the bridge from almost certain disaster. But to complete this groundbreaking structure, its engineers will still need to battle nature and will again need history's innovators.
This type of oscillation would be very worrying to the designers. The structure could collapse due to oscillations such as this.
To create even more impossible engineering. Engineers of the almost 3-kilometer-long Rion-Antirion Bridge faced huge environmental and geological challenges. In one of the most seismically active regions in Europe, cutting-edge technology safeguards the bridge from earthquakes. But the Rion-Antirion's designers and engineers face another massive environmental challenge.
We are like inside the wind channel here, so there is always wind. Thing is that as you go higher and higher from the sea level, the wind is getting higher and higher, the wind speed.
To protect the massive structure, engineers will need to take a lesson from history. When the Tacoma Narrows suspension bridge opened near Seattle, USA in July 1940, it was thought to be at the forefront of bridge design. But very quickly it became clear there was a problem, and it led to it being nicknamed Galloping Gertie. Just 4 months after its opening, despite a relatively low 40-mile-per-hour wind, the bridge's twisting motion became so violent that the bridge deck suffered a catastrophic failure and crashed almost 200 feet into the waters below. An inquiry found the wind was hitting the solid edges of the deck, creating an unstable oscillation that fed off itself, amplifying to the point of disaster. In the Greek Gulf of Corinth, the wind conditions are far more severe than for the Tacoma Narrows Bridge. The mountainous landscape creates a funnel where winds of 70 miles per hour are not uncommon. The aerodynamics of the bridge deck are crucial.
One of the solutions is to put fairings, spoilers. The same thing on a fast car, you have the spoilers underneath just to improve the aerodynamic shape of the fast car that drives through the wind. Here is the wind drives through the bridge.
These fairings safeguard the deck from gusts of over 150 miles per hour. But the massive cables holding it up also need to be strong enough to survive this extreme environment. The designers of the Greek bridge will need to draw on an innovation from history that conquered a challenge similarly once thought impossible. the second half of the 19th century, the growing metropolis of New York was being stunted by the wide waterway of the East River. Until then, the only way for people and goods to cross from Brooklyn to Manhattan was by ferry.
You see here Manhattan to my left and Brooklyn to my right. At the time, you could imagine just a river teeming with boats.
But in 1867, traffic suddenly ground to a halt.
A cold spell actually froze the East River over and essentially halted commerce because you could walk across the East River at the time on the ice, but you couldn't actually trade. So it was at that point when voices really kind of mounted, demanding a permanent kind of structural connection between the two cities with a bridge to have this lasting connection so that you could have reliable transportation and trade.
The man given the job was German-born engineer John Augustus Roebling, and what he designed still inspires fellow engineers today.
Just the concept of actually spanning over such a long distance at such a height was earth-shattering. No bridge had been built even close to this span.
The Brooklyn Bridge, completed in 1883 and spanning over 1,800 meters, was made possible by Roebling's revolutionary use of a new material, steel.
Just thinking of actually building a bridge, not of masonry as you would find in kind of traditional European style, but saying we have this new material, steel, we'll build the entire deck and the cables of steel. This is an absolute engineering marvel.
Steel was stronger, lighter, and more flexible than iron. But Roebling decided to exploit its properties even further in the bridge's 4 mighty suspension cables. By bundling together hundreds of parallel steel wires to create super strength and super safe cables. At Columbia University's Engineering Testing Lab, engineer Adrian Brugger can demonstrate just how much safer this technology is.
This cable is made up of actually independent, small 5mm circular wires. In this case, there's 9,000 wires. Those wires are then grouped into what we call strands. You actually take those and you compact those into the cable. This is a kind of a huge leap from the technology we had before, because before what we had was more or less serialized systems, such as chains or these large eye-bars, where if one of these eye-bars failed, generally that meant that the entire bridge failed. If one of these wires happens to be bad or has a crack in it, then the entire cable still has 8,999 other intact wires.
To compare the system used on the Brooklyn Bridge with what came before, Adrian will use the university's giant universal tester.
And more or less, a universal testing machine just means that it's a machine that is built to crush things and rip them apart.
First to be tested will be a solid steel bar.
This will be very similar to what you would have on an old bridge pre-Brooklyn Bridge, for example.
The steel bar has been weakened at a specific point and will be stretched under massive tension to simulate a fail on a bridge.
So we expect this bar to fail at around a good 200 tons. Right now you can see the necking is starting at about 1/4 up from the reduced section, so exactly where we wanted it. And it'll become more and more pronounced kind of as we see it now. The energy release was massive, and now the specimen is just catastrophically failed. It's broken.
Such an explosive failure could result in the collapse of a whole bridge, as tragically happened with Silver Bridge in Ohio, causing the loss of dozens of lives. Next, a multi-stranded steel cable is locked into place. This time, as it is stretched, it's subjected to extreme heat to weaken it and simulate a fail.
So we are seeing this cascading failure right now. You can see each wire is actually breaking one after another. It's not just this one catastrophic failure, but rather this cascade.
Unlike the sudden failure of the bar, when the cable starts to fail, the remaining wires take up the load. And even if all the wires were to fail, the energy released is gradual rather than one huge explosion.
So what you saw there was, exactly why the suspension bridge wires are such a great solution, but you can see that you didn't have this one catastrophic explosion and just failure of the member, but rather each one of these wires actually broke.
This steel technology enabled John Rubeling to design what was then the world's longest and strongest bridge, and an iconic engineering masterpiece.
This bridge would eclipse every other structure in the entire America. So it would be the tallest structure anywhere. So just a person actually standing on the tower would be on essentially the first skyscraper in the United States.
"55 meters above the Gulf of Corinth." Similar technology to that used in Rubeling's historic Brooklyn Bridge keeps the ultra-modern Rion-Antirion Bridge from crashing into the water.
Every cable is made by individual strands. They are parallel. Each strand is 50 millimeters diameter, more or less. Each strand carries more or less the same load. The only thing we do as the cable gets bigger and bigger, we put more and more strands, from 37 strands in the small cables up to 73 strands in the longest cable.
But here, the strong winds mean the cables themselves need extra protection. At a wind tunnel facility, Professor Luke Bisbee is about to see just how destructive wind can be.
All right, so we're going to start it up and we'll see what happens. If this were the cable in a real bridge, this type of oscillation would be very worrying to the designers, because what this would mean is that the metal that forms the cable would be being stressed repeatedly back and forth, and eventually in a metal cable that can lead to fatigue, which can cause cracking, and hence potentially failure of the structure. So the structure could collapse due to oscillations such as this.
When the wind strikes a cylindrical structure like a cable, it separates, then rejoins on the other side, causing the structure to oscillate, a hazardous phenomenon known as vortex shedding. Over the years, this dramatic effect has caused the collapse of several large cylindrical structures, such as chimneys and towers. In 1957, pioneering British scientist Christopher Kit Scruton realized that adding a simple fin to cylindrical structures would break up the wind vortices and reduce the vibrations that could lead to failure. He called it the helical strake.
Just seeing a little bit of vibration here, not too much. This is really incredible that this simple spiral can completely prevent the motion of this simulated bridge cable. With the helical strake, we get this disruption of the flow pattern, we introduce some turbulence, and both the formation of the vortices and the vibration of the cable both stop. The helical strake seems to be working. Since Kit Scruton invented the helical strake back in the 50s and 60s, it's been applied to tens of thousands of structures and chimneys and bridges around the world, and has really saved them from potential catastrophic collapse due to wind effects.
Scruton's helical strakes are integrated into every single one of the 62 kilometers worth of cabling on the Rion-Antirion Bridge. These, combined with the spoiler-like deck fairings, make this bridge as windproof as any on Earth. But to top off this wonder of impossible engineering, its designers would still need to look to the breakthroughs of the past.
It's a dream, this position. I never realized that it's so beautiful, so slender.
The stunning Rion-Antirion Bridge in Greece is one of the wonders of the engineering world. Built in one of Europe's most active seismic zones, its designers have not only had to engineer it to repel earthquakes and high winds, but also build it in deep water on substandard soil. The underwater construction may be an enormous mass of heavy concrete, But above water, the designers needed to create an elegant bridge that added to the landscape around it rather than scarring it. And to do so would require combining strength and beauty in an extremely hostile environment.
The pylon are the elements that at the end of the day will take most of the part of the earthquake. It is the pylon responsibility to take those loads down to the foundations.
It's a challenge that may have been impossible without one of the great engineering innovators of the past. In 1928, renowned Swiss civil engineer Robert Maillard won a competition to design a bridge linking two remote towns, 90 meters above the steep Salgina Valley. The result was the Salgina Tower Bridge. Designated an international engineering landmark, Maillard's bridge proved to the world that concrete could be both practical and beautiful. Engineer Urs Meier has been a lifelong fan of the iconic structure, but for the first time is about to see it from an entirely new perspective.
Up to now, I have seen the bridge from the deck, from the side, admiring the bridge. And now I have the chance to see the arch very close. I'm very, very happy. From here, I really can appreciate the structure. From this location, we have a very nice close-up. Nobody else can have. Maillard was a master in designing such slender elements, like columns, like arches. It's a dream, this position. I never realized that it's so beautiful, so slender. Must have been fascinating, dramatical to build such a bridge above this gorge. Maillard was the very first who realized the potential of steel-reinforced concrete. And this here is his masterpiece.
Building a bridge in this remote part of eastern Switzerland required great ingenuity.
We live here in a wonderful environment, but more often there is storm here, there is snow, there are avalanches, there are landslides, and Maillard had to face all these dramatical challenges to construct this bridge.
Concrete is strong in compression, but reinforcing it with steel bars also gives it strength in tension and allows it to be manipulated into almost any shape. Maillard designed an elegant three-pinned hollow box arch supported by reinforced concrete columns. This made it strong enough to transmit the bridge loads to the foundations, but with the flexibility to absorb any ground movements that could cause dangerous cracks to form. And Maillard's sleek design used less reinforced concrete, making it cheaper to build. But some were still skeptical.
At that time, there were no similar bridges of this size. People did not believe that this would work. But Maillard had already such an excellent name, not only in Switzerland, also abroad, that they trusted him and said, okay, go ahead.
When it opened in August 1930, the Salgina Tower Bridge was hailed in engineering and artistic triumph, showing concrete bridges could be both functional and beautiful.
Concrete is often having a bad name, and people think it's an ugly material, ugly application. And this application here proves that this has not to be the case. Maillard proved that design of a bridge is art.
1,000 miles away in Greece, my art's influence can be seen at the Rion-Antirion Bridge. The pier heads consist of 4 slender reinforced concrete pylons that combine cost-saving minimalism, flexible strength, and elegant design.
So from the bottom it's huge, and as we go towards the top we try to make it more elegant for aesthetic point of view, but also for saving of material and for saving of mass. At different locations of the bridge you will find different type and different qualities of concrete. The higher the quality, the more expensive it is.
Its 780,000 tons of uniquely engineered reinforced concrete ensure this bridge could survive an earthquake of 7 on the Richter scale.
You start the 4 pylons that you see, and then they connect at the top to the pylon head, a very critical element that takes the loads carried by the cables to the top.
The Rion-Antirion Bridge has not only redrawn the map of Greece, it has rewritten the rules of bridge engineering forever, and stands as a testament to the people past and present who designed and built it.
Floating a huge structure of 80,000 tons for months and keep building it in floating positions, or transporting this structure or putting at the right location, meeting the last piece of the deck or the doping span, these things look impossible. And then as long as you keep walking and get closer and closer, then you see you can be close to the millimeter and they fit together.
By drawing on the innovations of the past, adapting, improving, and making groundbreaking innovations of their own, the engineers and designers of this incredible bridge have succeeded in making the impossible possible.
Myself, I'm coming from the north part, and I experienced many times while I was traveling as a student, having to go all around, to go to Athens, see the bridge, employs around 100 people. It fills me with pride because for me, we are a big family and we all work together. That's how I feel.
The most technologically advanced skyscraper on the planet.
Look at this super tower, 632 meters tall.
Built to withstand earthquakes and typhoons.
I still feel like it's a dream. It's still unbelievable.
And the pioneering historic designs.
This is just amazing. This is real engineering happening here.
That made the impossible possible. Shanghai is a megacity. With 24 million inhabitants and rising, it's one of the most densely populated cities in the world, with ambition to match.
Shanghai will always be one of the international cities in the world and one of the most important ones in the world.
This global financial center holds 10,000 people per square mile, and the only place left to build is up. In the mid-1990s, development began in an area of farmland on the East Riverbank, known as Pudong.
If you look at Pudong today, 20 years after it is being transformed into an international center for business from a quiet farmland, and today is even dominated with a lot of new high-rise buildings.
In November of 2008, work began on the most impressive of them all. At an astounding 632 meters, the Shanghai Tower will be the second tallest building on Earth, the tallest in China, and one of the tallest ever built in a seismic zone. It will be the most advanced building of its kind on the planet, with 128 floors and 9 indoor gardens, where 16,000 people will work, sleep, and shop, making it a true sky city. And yet, this is one of the most difficult places on Earth to build a skyscraper.
Building a super high-rise building in Shanghai is quite unique because you have to deal with the wind load and also the earthquake load.
For Dennis Poon and his fellow engineers, it's a seemingly impossible challenge.
I cannot believe that today we're designing the tallest building in China and also the second tallest building in the world.
The engineering complications begin at this mighty tower's roots. Because not only is Shanghai an active seismic and typhoon zone, but amazingly, this megacity is sinking into the soft soil below. The land under this massive metropolis is deflating like a giant air mattress, as its shallow water table collapses under the weight of its modern buildings.
For the Shanghai Tower, one of the biggest challenges is the foundation to support this super tall building. With its weight of 850,000 tons, how do you support it in the soft soil condition, which is locally in Shanghai?
The solid bedrock is 200 meters down, with Shanghai itself wallowing on a soft layer of sand, clay and soil. A geotechnical nightmare ready to swallow an 850,000-ton building like the Shanghai Tower.
So we have to design and build this foundation for the tower to deal with these challenges.
And the engineers only have one shot, as constructing a tower this tall leaves no room for error.
For a super tower, of course, the whole design challenge is to do the foundation right, so you don't have future problems, because you can't fix it later.
The engineers will have to look to the great innovators of the past to defy this seemingly impossible challenge. Once upon a time, the modern world of skyscrapers was inconceivable. Early man was limited by what nature would provide. And for the ancient Egyptians, taller had to mean wider, and an awful lot of manpower. Unless you believe in some of the more otherworldly theories. And when it's come to building towers, the ground below has frequently thrown a spanner in the works.
Mamma mia!
In order to create a skyscraper 11 times taller than Pisa's famous Leaning Tower, the designers of the Shanghai Tower will need to draw on the inspiration of 19th century engineering pioneers. The US city of Chicago is home to one of the world's most iconic skylines. But just over a century ago, engineers were faced with a challenge that meant building any higher than just a few stories above street level was a near impossible dream.
You wouldn't know to look at it, but Chicago is actually one of the least logical places that you could ever attempt to build a skyscraper. We've got soil here that is incredibly squishy. Underneath this kind of shorter, smaller layer of earth, we've got a very, very deep layer of soft, squishy clay. This is a really difficult thing to build a skyscraper on, of course, because when you load the building's going to sink.
As property in downtown Chicago grew ever more valuable and the city began to boom, the need to grow higher and maximize space posed engineers a problem. Taller buildings would mean heavier buildings, and as they had discovered, there was a limit to the weight that the local soil could take.
This is the auditorium building of Roosevelt University, designed by Adler and Sullivan in 1889. It's a national landmark and so important to Chicago as well.
The building is 72 meters high. When it was completed in 1889, it was the tallest building in the city, one that would have been unthinkable just a few years earlier. And the radical innovation that made it possible came from engineer Dankmar Adler.
We're headed down to see Adler's specially designed foundations to deal with the soil here in Chicago.
Previously, the whole weight of a building would bear down on its walls, which would sink into the clay like a cookie cutter. Adler's innovation was to use wood and steel crossbeams encased in concrete to create a reinforced concrete raft that the 110,000-ton building sits on.
I'm going to illustrate what's happening here with this piece of modeling clay used to represent the clay that's under our feet here in Chicago, this sort of peanut butter jelly-like substance. The clay is really quite deep, and the bedrock doesn't start in Chicago until 75 to 100 feet below the surface. So I've got my chopstick here to sort of illustrate, and I take my structure and I go through the hard pan, and they just didn't have the technology in the 1880s and the 1890s to excavate that far down to bedrock. So instead, architects, engineers here in Chicago are coming up with new ways to solve this problem. The method that we're standing on here is sort of the equivalent of this kind of penny that I'm going to illustrate. So this pad or this raft is put down, and then the building, the column on top of that is put on top of that. And you can see that I can push it down a little bit into the clay, but not really that far. This is distributing the load.
Adler's revolutionary engineering solution made building on substandard ground possible. And today, the city's tallest building, the Willis Tower, rises 442 meters, more than 6 times the height of Adler's auditorium. But despite its influence, the auditorium's design wasn't 100% perfect.
So on the north edge of the building, we've got this large, heavy exterior walls that are much heavier than what's happening on the interior of the building. And we can see the challenge with that, the fact that this is much heavier and this is much lighter in the building, with this long crack here in the floor. And we can also illustrate that pretty well with these marbles.
Although the Shanghai Tower would be impossible without the innovation of reinforced concrete raft foundations, its engineers cannot afford for it to subside like the 19th century Chicago auditorium.
If the building does not settle uniformly, it will tilt. This is something we cannot afford and we don't want to see, because the building is so tall, a slight tilting will cause a big deflection on the top.
To overcome this potentially catastrophic risk, the engineers will have to take Adler's ideas and supersize them. In 2008, a 2-year operation to build the foundations begins. First, they sink hundreds of deep supporting piles into the soil, then begin pouring the raft or mat foundation.
Construction of the mat foundation so deep below grade is a big challenge.
It takes a world record 60 hours of continuous pouring to create the mat, a process involving 2,000 workers and 450 concrete trucks.
We basically use almost all the concrete trucks in Shanghai, and finally we overcome this challenge.
All in all, the mat soaks up 61,000 cubic meters of concrete, another world record.
61,000 cubic meters is a lot of concrete, and comparable to the Hoover Dam many years ago in the States.
Without the pioneering work of engineers like Dankmar Adler, building a tower this high in Shanghai would have been an impossible dream.
You can see the sheer scale of this tower, and you can imagine how big the foundation we need to support this tower in a soft soil condition. And we get it done right, look. I even cannot believe it.
But in creating this ultra-modern skyscraper, its builders still face major challenges, and will have to draw on innovations from the past.
This is arguably the world's first skyscraper
to produce more impossible engineering. Begun in 2008, the Shanghai Tower will be the most advanced skyscraper in the world, the tallest building in China, and the tallest ever built in a seismic zone.
This is a fantastic piece of engineering. We are all grateful that we have the opportunity to work on this iconic project.
The tower is a massive 632 meters tall and will consist of 128 stories of cutting-edge engineering and contain gardens, shops, hotel, office space and residential accommodation.
To build it and also overcome many engineering challenges, it's still, to me, it's quite incredible and unbelievable.
But in creating a building this immense, the architects and engineers have set themselves a seemingly impossible challenge. Each floor weighs an average of 6,500 tons, making the building enormously heavy. The structure itself has to support a total of 850,000 tons.
For a super tall building, you have enormous forces to support. We're not building a house, we're building a 128-story building, the second tallest building in the world.
It's a challenge that would have been impossible if today's engineers weren't able to draw on the great innovators from history. Once upon a time, the maximum height of a building was determined by the thickness of its walls, because the weight of each story had to be supported by the floors below. It meant tall buildings remained the realm of the rich and powerful. Medieval religious architects enabled thinner walls and large stained glass windows by using external supports called flying buttresses. But these also made buildings grow sideways and were still the preserve of the wealthy church.
Bless you, my child.
But there was a revolution on the horizon. And this seemingly innocuous and picturesque region surrounding the River Severn in England was the crucible of it all. Shropshire was at the heart of the Industrial Revolution, the Silicon Valley of the 18th and 19th century. Its engineers were at the very cutting edge of technology because they had mastered the production of iron.
This area gave birth to some of the greatest engineering pioneers of our time and enabled the construction of iconic structures like this Iron Bridge, the first cast iron bridge of its kind in the world.
But just a few miles upriver is a somewhat less iconic, but arguably much more significant building.
It wasn't until about 20 years ago that the historical importance of this building was properly understood, which is why it's fallen into disrepair.
This crumbling red-bricked mill is one of the most important buildings in the world.
This incredible but rather sad and dilapidated building in Shrewsbury is arguably the world's first skyscraper. It's the first time that iron was used in a multi-story frame construction, and it really paved the way for tower blocks and skyscrapers that we know today.
Built in 1796, Ditherington Flax Mill was the brainchild of engineer Charles Babbage. And he drew on the region's groundbreaking use of iron to build the first metal-framed building on the planet.
Previous to the iron frame, the taller the building, the thicker the walls had to be to support them. But with Babbage's design, the walls could be thinner, which meant that the rooms could be much larger. It also meant that you could design buildings much taller.
In Babbage's design, all the weight of the building was borne on its iron frame. So none of the walls were load-bearing, making the sky the limit for the first time.
This main building had 5 floors, including this attic, which was previously unheard of. It had a working area of over 2,800 square meters, or 31,000 square feet. And these narrow, relatively lightweight metal beams would be able to support much more weight than the solid brick walls of previous buildings.
This simple but brilliant engineering solution meant that Babbage's flax mill was the forerunner of almost every large-scale building in the modern world.
What Babbage achieved in this building was truly remarkable.
In building the Shanghai Tower, its engineers are employing the same principles as Charles Bagge's 5-floor flax mill, but on a whole new scale. The 128-story building, however, will have a steel frame instead of iron.
The advantage of structural steel is it's lightweight, it's high strength, and easy to erect, and can be prefabricated in the shop with better quality control.
Because the steel bears the weight of the structure, the external walls no longer need to be load-bearing. They don't even need to be flat or straight. They can be made from a variety of lightweight materials, such as glass. And architects can mold them into any shape they want to express their vision. Zheng Xia was one of the lead designers on the project.
When you on the city looking at this building, different view you look at, the building looks different shape. The movement looks different. You feel like it's alive, something alive organism, you know, because it's don't feel like it's a dead, just a cold object.
The whole building is clad in a series of glass walls, each of which can be suspended over many floors like a giant curtain, thanks to the strength of the steel rods that hold them in place.
We're at the top of the 101st floor building, and you can see the curtain wall is being hung 14 floors above us.
Between the curtain wall and the inner core, which houses offices and hotel rooms, the designers have allowed the building to breathe, creating a massive open atrium, only possible because of the building's lattice-like steel frame.
Here we are standing on the 8th floor of the building. You don't want to block too much sunlight to a massive structure. It opens up the airy feeling.
Yet despite the use of super lightweight materials, the Shanghai Tower weighs in at a staggering 850,000 tons. And to stand up to Shanghai's triple whammy of high winds, earthquakes, and substandard soil, the designers would have to reach for the history books again.
Ready whenever you are, Rich.
With 24 million inhabitants, Shanghai is one of the most densely populated cities on Earth. And the only way of expanding its globally important financial center is to reach for the skies. 632 meters tall, the Shanghai Tower is being built as a living city in the clouds. It will house offices, shops and hotel rooms, as well as conference and concert halls.
If we turn this building down, it's going to be 600 meters long, about 6 urban blocks. So in a way, we think each of this zone is a communities.
But in creating a super tower in which 16,000 daily users will work, rest and play, its designers have set themselves a lofty challenge. How to transport its population around this massive structure.
Who wants to come up to a 100-story building and work up there? I can see many office buildings with a huge crowd in the lobby.
It's an engineering feat that would be impossible without one of history's great innovators. By the mid-19th century, the world's skylines were still relatively skyscraper-free. For one reason, no one wanted to take the stairs. Unlike the penthouses of today, the higher you lived, the poorer you were.
Mustn't grumble.
Steam-powered and hydraulic lifts were being used in mines and factories for freight, but they were too dangerous for people. The ropes on the pulley system were inclined to break. But city skylines were about to change. Thanks to a man named Elisha Otis, in 1852, he came up with an idea that revolutionized the world of construction, pioneering a simple mechanism that changed the way we use tall buildings forever.
So we're here in Bristol, Connecticut at the Otis Elevator Company test facility. This is where they test the newest elevators that they're going to install in buildings across the world. But they also have this replica of a device that Elisha Otis first constructed for the Crystal Palace exhibition, the World's Fair that ran from 1853 to 1854.
The World's Fair was the perfect shop window for Otis, who was a showman as well as an inventor. He knew that the eyes of the world would be upon him if he could prove that his idea for protecting passengers was safe as well as practical.
So I think it's important to remember that Otis didn't invent the elevator. Certainly there had been ways of moving goods and people up and down from floor to floor using hoists and pulleys for centuries. But what Otis did do was to recognize that people were afraid of going into an elevator. So at the 1853-1854 World's Fair, he builds this device to provide a brake, a safety, in case the rope broke.
With his showman's hat on, Otis decided the best way to prove his idea was to put it to the test, using himself as a guinea pig. In front of an expectant audience, he stepped onto the platform, rose above the crowd, and gave the signal for the rope to be cut, a potentially fatal step.
So let's see if Mr. Otis's invention still works. Ready whenever you are, Rich.
The system features a wagon spring, which is held up by a rope which keeps it in a state of constant tension. When the rope is cut, the tension in the spring is released, which causes pins fixed to the side of the spring to lock into a ratchet located in the wooden frame. This brings the elevator to a complete stop, preventing it from falling and injuring any passengers.
And all these years later, every single elevator today around the world has a similar safety device that is allowing passengers to feel safe in tall buildings. And I didn't plunge to my death.
Otis's invention transformed the world's skylines, and cities like New York that couldn't expand sideways could now reach for the skies. Fittingly, in 1913, it was the Otis Company that were commissioned to provide the lifts for one of New York's most iconic skyscrapers, the Woolworth Building.
By 1916, more than 100,000 people had paid their 50 cents to ride the elevator to the observation deck at the top. And now, 100 years later, those original Otis elevators are still being used to carry office workers up and down.
Otis's invention meant that instead of the poor being consigned to the building's upper levels, the value of floor space now increased as you went higher. Penthouse living was what everyone dreamed of.
As we drive through New York, it's easy to forget, I think, that within just a short span of time, just about 160 years, all of these skyscrapers have been constructed. And so the rise of the elevator and the rise of the skyscraper are so closely linked.
Otis's first passenger elevator traveled at 0.2 meters per second. At that speed, it would have taken nearly an hour to reach the top of the Shanghai Tower.
Look at outside. We are more than 100 stories above ground. You can see the magnificent view. For this tower, we are using the world's fastest elevator traveling at 18 meters per second, which is faster than the speed of a car traveling at normal cruising speed.
In all, the tower has 106 elevators, single and double-deckers, including the world's furthest traveling single elevator at 578.5 meters. And along with the residents, shoppers and office workers, will transport thousands of tourists to its top floor observation deck.
We are on the street level right now. You see this 128-story building. The view at the top of the Shanghai Tower will be unique. And when it's all done with the elevators, you can get up from the ground floor to the top up there in 35 seconds. Marvelous.
The Shanghai Tower's 632-metre elevation won't only provide stunning views of the metropolis below, it will also present a massive obstacle to the wind. Shanghai is in a typhoon zone, and defending the tallest building in China from the immensely powerful and potentially devastating winds that sweep through the city is a major challenge to the engineers.
On the 100th floor, the wind load can be up to 94 pounds per square foot, which is almost 4 kPa. So it's a huge wind pressure. How do we resist this wind pressure?
Creating this giant piece of engineering would be impossible without the great innovators of the past. The first wind tunnel was constructed in 1871, a full 30 years before the Wright brothers' inaugural powered flight. But they had always been very much geared to aeronautical engineering. That was until brilliant engineer Jack E. Cermak evolved the technology to enable the world's skylines to grow ever higher.
In the late 1950s, Cermak and his contemporaries pioneered the use of new wind tunnels.
Professor Rhys Morgan is visiting wind engineering firm RWDI, who have drawn on Jack Cermak's innovations, which included much bigger tunnels than for aeronautics and used irregular shapes to mimic the unpredictable winds that can hit cityscapes.
Blocks like these on the floor create the kind of turbulent atmosphere, the turbulent winds that you see in cities and urban environments. So they're perfect for testing structures that we want to build in cities.
One of the early skyscrapers to be tested in Cermak's wind tunnel was New York's World Trade Center, then the world's tallest structure. The innovations that resulted feed into the design of every new skyscraper, including the Shanghai Tower. A scale model is being placed into a mock-up of the London skyline to demonstrate how wind can dangerously affect tall buildings.
Wow, it's really windy.
As the wind rushes past the structure, it forms into eddies of low pressure on either side.
So the wind is coming in here, it's hitting the side, and then as it comes around the corner, it produces a low pressure region here. And that causes the building to move this way. But then that means that the wind coming around this end starts to cause a little bit of movement this side and low pressure. So we start to get this low pressure, low pressure, low pressure, low pressure, and that causes this oscillation back and forth. This is just amazing. This is kind of, this is real engineering happening here. That's moving a good 5 centimeters either side. I wouldn't want to be on the top of this building if it was a real building in the city.
For architects like those that designed the Shanghai Tower, the challenge is to come up with a shape that reduces those vortices.
Okay, let's try this one.
This time, the building is tapered like an elongated pyramid.
And you can see there's very, very little movement. Let's turn it up a bit more. We're running at 3 times the wind speed of that very first model that we saw. And the building's just not moving anything like as violently.
Because of the tapered shape of the building, the wind creates vortices of different sizes at different heights.
It's causing some oscillations down here, but they're much slower than the oscillations occurring at the top end.
That means that different parts of the building are trying to shake at different rates, with the net result, in this case, that they cancel each other out.
And so it prevents the building from oscillating quite so violently.
Jack Cermak's invention has allowed city skylines around the world to change radically. Today, no one would think of building a skyscraper without first testing it in a wind tunnel. The Shanghai Tower is tapered, but it also has a distinctive twist, which is directly influenced by tests like this. The design reduces wind loads on the building by 24%.
The twisting of the building is a great example for engineers that can combine creative architectural design with good engineering. When we work together in tandem with each other.
The architects also designed a notched V running the entire length of the spiral.
Number one, if the building is continuous spiral without this V, you don't understand the spiral as much. Once you have this break of the V, you can actually read the building moves, the spiral shape, much better, clearly. Number two, we actually make this as an entry to the office zone. So it's very visible, very easy to remember, right? People don't get lost. And number three, eventually, we make this all LED graphic. So it's like a river runs through it. It's very, very cool.
The notched V shape started out as an architectural flourish. But when they tested it in the wind tunnel, the designers of the Shanghai Tower made a discovery as welcome as it was unexpected.
This notch also helps to cut down the turbulence effect or the vortex shedding of the building. So the tapering shape of the building helps the aerodynamic, the twisting helps, and the notch helps. And at the same time, the tapering also lowers the center of gravity of the building. That gives us more stability. The lower the center of gravity, the more stable the building is.
But the Shanghai Tower faces a natural force potentially even more dangerous than typhoon winds. And yet again, the engineers will need to call on the great innovators of the past.
大きな地震、それから強い台風に耐えてきました。これ本当に素晴らしいことだと思います。
To make this impossible skyscraper possible. Started in 2008, the Shanghai Tower will be the most advanced skyscraper in the world. And the tallest building in China. And in creating this record-breaking super tower, its engineers are having to overcome seemingly impossible challenges. But the Shanghai Tower faces another potentially devastating natural phenomenon. Shanghai is in a level 3 seismic zone.
Shanghai Tower is the second tallest building in the world. Of course, we're not only designing this building for typhoon wind load up to 120 miles per hour wind load, we also have to design it for significant and severe earthquake.
To overcome the challenge, its engineers will have to look to history's great innovators. Earthquakes are among the most powerful of all natural disasters, leveling buildings and triggering tsunamis. Neighboring Japan is the most seismically active country on Earth. For years, no one could understand why regular buildings would collapse in earthquakes, while traditional pagodas stayed standing.
この五重塔、当時の五重塔は高さ51メートルですね。日本で一番高い五重塔です。それがこのように約400年間大きな地震、それから強い台風に耐えてきました。これ本当に素晴らしいことだと思います。
Modern studies of pagoda design eventually revealed the secret.
まず第一に非常に柔らかい構造ですよね。多くのジョイントがあって、それから食い物もありますし、柔らかい構造なんですね。ですから、地震が来ると、スネークダンス説というそういう説を唱えた先生もいますけれども、要するに蛇がこうね歩くように、そういうような例えで強度を示すことがありますけれども、くねくねとこう強度をする。
Pagodas are typically 5 floors high, but each floor is capable of moving independently, so when a quake strikes, its snake-like pattern keeps the center of gravity more upright than a rigid building would. The wooden joints that support each floor consist of several separate components, so each part can slide and move, and the friction they create acts like a damper to soften that movement.
接合部が多くの接合部がところでエネルギーをですね吸収するというシステムを持っているわけです。
The whole of the Shanghai Tower has a very similar template to that of a pagoda. The structure is divided into 9 vertical zones around a central composite steel and concrete core. Huge perimeter columns and outriggers are also fixed to the central core to further brace the tower against natural disasters.
The core is just like the main trunk of your body, and the two column, the exterior column outside is like the ski post. And this steel truss member is connecting your body and the column, giving you a much better stability for the building to resist earthquake.
The earthquake-proofing measures extend from the base of the tower right to its tip.
Here we are, coming up to the 125th floor of the tower, which is one of the most important rooms in the building.
So what is it that makes this such a key part of the structure? The answer is suspended above Dennis's head.
You can see we have a 1,200 tons of steel block being hung 4-story above us.
So why would engineers take up valuable floors and sacrifice the revenue they could generate with a steel block the weight of 600 family saloon cars? Boston's John Hancock Tower, 60 stories high, was completed in 1976. Its then futuristic glass-clad design anticipated the skyscrapers we know today. When it first opened, upper-floor occupants complained of motion sickness as the building swayed in the wind. This came to the attention of an engineer, William Le Mesurier, who came up with an ingenious solution.
What I've got here is a very simple model of a skyscraper. It's a beam structure going up several stories.
Turning a handle at the base of the structure mimics an earthquake.
With steel-structured buildings and glass buildings, of course, we're reducing the weight of those buildings, so you can actually go much taller, you can build them much taller. But then you do have this problem with sway.
Le Mesurier's genius was to find a way of counteracting and cancelling out the swaying of the John Hancock Tower. He took over the 58th floor and installed 2 steel boxes, each filled with several hundred tons of lead and resting on a steel plate.
You have to imagine this is an 800-ton weight that I'm lifting up onto my skyscraper now, and I'm just going to tie it to the top of my structure.
The tuned mass damper, or TMD as it became known, had a dramatic effect.
It's amazing. The structure is hardly moving. I mean, it's quite phenomenal. So what we're seeing here is the mass damper oscillating out of phase with the vibration of the structure. In a building like this, you wouldn't have an 800-ton ball flying around violently and smashing into the walls and things.
The principle is simple. As the building sways one way, it pulls the damper with it. As the building starts to sway back, the damper is still travelling in the opposite direction, so it stops the building from going too far.
It's amazing how much of an impact it has. It really does just stop the structure from swaying around. Without tuned mass dampers today, we just wouldn't have any of the kind of mega structures that we have.
As buildings have got taller, so the dampers have got bigger.
We are walking to the upper portion of the TMD system, 2 mass damper system. Without this 2 mass damper, we have to use a lot more structural steel and material to stiffen up the building.
So despite taking up 5 of the tower's 128 floors and weighing over 1,000 tons, it actually made the building cheaper and lighter to construct. It's taken 15 years of planning, design and testing, and 7 years of construction to raise this super tower from its foundations deep in the Shanghai soil to the tip of its 128th floor. But by drawing on the innovations of the past, adapting, improving them, and making groundbreaking innovations of their own, the engineers, designers, and workers on the Shanghai Tower have overcome substandard ground, high winds, and earthquake risks, and succeeded in making the impossible possible.
Look at this super tower, 632 meters tall. It is exceeding my expectation and a lot of people's expectations.
The most audacious airport construction on the planet.
Kansai Airport Island was the biggest man-made island in the world.
Built at sea to withstand earthquakes and typhoons.
Of course, in Japan, we have many strong earthquakes.
And the pioneering historic innovations.
From an engineering point of view, for that time, it was high advanced technology. It's hard to imagine, I say.
That made the impossible possible. Because of its distinctive landscape, the island nation of Japan has some of the most densely populated areas in the world. With over 127 million inhabitants vying for precious space.
Geography is that Japan is a very heavily populated island. It's double the population of the UK, and although the island is bigger than the UK, 75% of it is mountainous, and about 50% of it is at 45-degree slope, so you can't live on that. So everybody's crammed into the coastal areas and the big cities.
So when it was decided that Japan should attempt to build their first 24-hour airport, it presented its engineers with a unique challenge.
We did not have any space for the airport because almost all the land was very heavily populated. And then there are many residential houses and then the factories.
Their radical solution? To create new land where previously there had been no land at all.
They had no choice. If you wanted the airport to be where people could get to it, it had to be within reach of Osaka. The logical conclusion to that was to go to the difficult place of the Osaka Bay.
They would attempt to create an entire island from scratch, something that had never been done on this scale before.
There was risk, real risk, in trying to build something so big and on such an ambitious scale.
Building in Osaka Bay would mean tackling one of the most hostile environments on Earth. With typhoon winds a regular occurrence.
We have many typhoons coming all region in Japan.
The maximum wind velocity is more than 50 meters per second. Heavy typhoons cause a very big wave, more than 3 meters.
Earthquakes are a constant risk.
Earthquake is often happen in Japan. Many very strong earthquakes.
And the geological conditions are near impossible.
Perhaps the biggest challenge of all is the weak ground. The ground under the sea at the site that was chosen was so weak that divers would sink into it if they stood on it.
Nevertheless, engineers decided to attempt a feat of impossible engineering and undertake the most ambitious land reclamation project of modern times.
Every project is a challenge, but there is an edge to it when you're stepping out of the known into the unknown.
But building an island at sea was an incredible ambition that would not have been possible without centuries of innovation. Creating usable land from open water has been a challenge throughout history. Prehistoric settlements in Scotland built huts in lochs called crannogs to house large families. Which was fine until the stilts rotted. In Peru, the Uros people of Lake Titicaca built villages on rafts of reeds to prevent attacks by their neighbours, the Incas. But the anchoring system was unreliable. And in the Pacific Ocean, the rulers of the ancient Sodalur dynasty built the offshore islands of Nan Madol from which to rule. But took their secrets of construction to the grave. Thankfully, a more permanent solution to creating new land was on the horizon. To attempt such a daring project, Japanese engineers sought inspiration from a 17th century Dutchman who solved a seemingly impossible land shortage problem of his own. The Netherlands is constantly fighting to keep the North Sea at bay. 1/3 of the land is below sea level, and 65% is vulnerable to flooding. Over the centuries, the country has suffered some catastrophic floods.
We always fight the water because we have to make our land safe. We have to live with the water, but also fight the water.
Today, the Netherlands has the most sophisticated water drainage system in the world. But in the 17th century, dry, usable land was so scarce, the growing population was running out of space to produce food.
They tried to drain these bigger lakes within the sea dike area and the marshlands in North Holland, but a lot of attempts they didn't work. These lakes, they were very deep. It took them several centuries to figure out how to drain them.
But in 1609, engineer Jan Andriaanzoon Leeuwarter came up with an ingenious solution. The son of a miller, Leeuwarter's idea would change the face of the Netherlands forever. Water engineer Nanko Dolman has come to Beemster-Polder, where it all began.
What Leeuwarter did here, in making this polder dry, was a big achievement, and it made him the first hydraulic engineer in the world.
This entire area was once a lake measuring 70 square kilometers and 3 meters deep. Traditionally, windmills were used for water drainage, but they had their limits.
The challenge with windmills like this, they can scoop off 1 meter per windmill.
But as the lake was 3 meters deep, Leeuwarter needed to rethink how the windmills were used. First, he dug a 38-kilometer ring canal around Beemster Lake. He used the excavated soil to create a barrier or dike. He then installed his first windmill, which lifted water from the lake and into the ring canal. What Leeuwarter did next was a stroke of engineering brilliance.
So in the first stage, they could move a scoop only 1 meter of water away. So they would construct and build a second windmill. This windmill would scoop the water, and it will be elevated to the next windmill, and it will be discharging to the ring canal.
The result was a series of windmills placed 1 meter below the previous one. As the water level in the lake dropped out of reach of one windmill, another was installed below. Thus, the water was lifted up in stages until the lake was empty. And the dike protected the new land from further flooding. Leeuwarter used 42 windmills in all. The project took 3 years to complete, and in 1612 the lake was empty and the land ready to cultivate. These reclaimed areas became known as polders.
The Beemster-Polder was the blueprint of all polders, not only for the Netherlands but also internationally, and it is a real engineering masterpiece.
Leeuwarter had made the impossible possible. Now 50% of the Netherlands is made up of reclaimed land, protected by over 12,000 kilometers of dikes and sea defenses. Engineers in Japan needed to take the Dutch principles of reclamation and go one step further. Where engineers in Holland drained lakes to create usable land, Masakai Kitazume and his colleagues would have to build upon land that was underwater and create an island.
So it was a very, very big challenge for us, for the engineers. We construct this island more than 5 kilometers from the coastal area. And also the sea depth was more than 20 meters.
But the biggest challenge was the soft clay ground underneath Osaka Bay. Extending 20 meters below the surface, this weak ground was one of the last places on Earth you would choose to build an island. The clay holds the water like a sponge, and, like a sponge, when you place a heavy object on top, it compresses as the water is forced out, causing the object to sink.
So the best of Japanese technology is required to strengthen that ground below the island, otherwise it would have just vanished.
Engineers knew, left as it was, the island would sink into the waterlogged sea floor. If they could not control how far the island sank, the project would fail. The solution they found was the sand drain.
Main purpose of the sand drain was to speed up the ground settlement.
Sand drains work by providing the water in the ground a shortcut to the surface. Sand is spread across the sea floor. Pipes are driven into it, also filled with sand. The pipes are removed, leaving sand columns behind. The weight of the island will compress the soft clay, squeezing water into and up the columns to escape into the sand layer. This means the island will still sink, but reach its natural depth in a quicker, more controlled way and settle on drier ground. A staggering 1 million 20-meter deep sand drains were installed, the largest operation of its kind in the world. The seabed was ready to take the weight of the biggest man-made island ever built.
The best case scenario was that all would work well and the island would stand, and the worst case scenario was that the whole thing would vanish into the seabed and just keep going.
But engineers had further challenges to face, and they would have to turn to the great innovators of the past.
What we take for granted in our days, that was first time done in this airport.
To produce more impossible engineering. Kansai Airport, Japan, is an engineering wonder of the world, built on its own man-made island in the deep and unpredictable waters of Osaka Bay. Its construction was a seemingly impossible challenge.
We have many technical issues we have to solve to construct this island.
After 2 years tackling nature's most challenging geological conditions, engineers had placed 1 million sand drains into the seabed to help stabilize the ground. But before they could begin the island, they had the daunting task of constructing an 11-kilometer seawall.
The maximum wind speed might be 40 or 50 meters per second, and then the wave height at the typhoon season is more than a couple of meters. So the seawall is one of the very important structures for the man-made island.
To begin, divers laid huge foundation stones onto the seabed. Loose rubble was poured on top to build the wall up above the height of the pounding waters of the bay.
If the seawall was damaged, the soils on the island will flow down to the sea.
To stop the rubble wall being eroded by waves and the island washing into Osaka Bay, designers would need to turn to the innovators of the past. In the 1950s, engineering genius Pierre Danel developed a system that would become the world's greatest defense against the pounding sea. At the Laboratoire Dauphinois d'Hydraulique in France, he and his team designed the coastal armor unit known as the tetrapod. At Tokyo's Waseda University, engineer John Batchelor has come to see a demonstration of how the tetrapods work.
There'll be waves at least 3 meters high in a big typhoon, and they pack a lot of punch. So it's very important that the edge of the island is not scoured away by the waves.
The university's wave tank facility can accurately recreate the typhoon conditions that regularly strike Kansai.
2 students down there are putting the model together. They're putting pink pebbles on one side to represent boulders, which would be a very traditional way of protection. And on the other side, they're putting tetrapods like this that link together. It's simulating waves that are about 3 meters high, which is what we'd expect from a big typhoon in the Osaka Bay. So we can see clearly from here that even just with one wave, quite a few of the pink boulders have been washed, some of them right over the island, whereas the tetrapods have all stood firm. And that's because the tetrapods, even though they were lifted by the waves, couldn't be pulled apart because of their shape.
The tetrapod shape also dissipates the force of the waves by allowing water to flow around rather than against it. Since their first installment in 1950, Danel's tetrapods have protected the world's coastlines. At Kansai Airport, tetrapods provided the perfect engineering solution. Nearly 50% of Japan's coastline now relies on tetrapods. The Kansai Airport seawall is one of the largest single applications in the world.
We installed more than 48,000 pieces of the tetrapod. This was a very, very huge number of the tetrapod.
With the seawall complete and protected against the elements, Kansai had a 20-meter deep, 4 by 2.5 kilometer lagoon. Now engineers had the phenomenal task of filling it. In a Herculean operation, 3 mountains were flattened to provide enough rock to fill the hole.
We used more than 180 million cubic meters of the rock on the soils.
80 ships worked for 3 years to ferry the rubble to the site and dump it into the man-made lagoon.
It was a very, very fantastic thing. So many special vessels working there.
In all, the infill was enough to fill 45 football stadiums to the brim. As the surface of the island was leveled off, engineers turned their attention to the terminal building itself. The structure would need to fulfill the requirements of an ultra-modern airport, but also withstand typhoon-strength winds and some of the strongest earthquakes on the planet. Awarded the challenge was architect Renzo Piano, one of those behind the radical Pompidou Center in Paris. And working alongside him was Japanese colleague Noriaki Okabe.
This program asked very big building, 1.7 kilometer building. So we must do something different.
As the island had limited space, there was only room to construct one supersized building which would fit all the functions of a modern airport under one roof. To complete this seemingly impossible challenge, airport designers would draw inspiration from the audacious work of a trailblazing architect of the past. 1930s Berlin was a time of huge change. Germany had grand ambitions, and the city was being overhauled to create a new, modern metropolis. Architect Ernst Sagebiel was commissioned to replace Berlin's old airport with a new one that would be seen as the gateway to Europe. What Ernst came up with would change the way airports were constructed forever.
Welcome to Tempelhof Airport. We are in the middle of Berlin right now, 2.5 kilometers from the city center.
Tempelhof has been described by architect Norman Foster as the mother of all airports. This 1.2-kilometer building, when constructed, was the longest building in the world. Bernhard Kortz is a German architect who has made a special study of this unique and historic airport.
So this is the main departure lobby, or also arrival hall. Imagine yourself being an air passenger at that time. You're not used to size that big. It was meant to impress all the passengers that would come from Europe, from all over the world. For our times now, it's not that impressive because we know huge skyscrapers, but this building was finished in '39, so at that time it was highest marvel of engineering in the world.
To create a building this large, Sagerbiel turned to the most cutting-edge techniques of the day.
From an engineering point of view, the whole hall is very interesting because for that time it was high advanced technology.
Sagerbiel used the relatively new system of a steel-reinforced concrete framework, which had incredible load-bearing strength. It was then covered in marble to create a vast, monumental space. But the airport was not only designed to make an impact, but to create a new system.
This building was just looking way forward into the future. This was the first airport that was really designed like an airport as we know it now. All the separation, what we take for granted, that was first time done in this airport.
Tempelhof became the most modern airport in the world. For the first time, there were different areas for passenger arrivals and departures, plus separate gates for each flight, covered by a unique metal canopy.
This is where your plane would wait for you. This incredible space is also an engineering masterpiece.
The canopy runs along the side of the building for 400 meters. Ingeniously, the weight of the canopy is counterbalanced by a steel wire hidden in the fabric of the building.
By using that construction, they could achieve a very thin and light structure. You have a huge spanning roof where you can actually enter with the whole plane. So even when it's raining or snowing or stormy, you can enter on dry foot. And additional, your luggage, you don't have to carry yourself. So the whole situation was just totally, completely different from any other airport at that time. It's hard to imagine, I say.
Tempelhof achieved what no airport had done before. It pushed engineering to its limits with its daring design and created a concept that would become the blueprint of all modern airports. "6,000 miles away at Kansai Airport, architects and engineers have taken this concept of airport design to a whole new level. Just like Tempelhof, when built, Kansai was the longest building in the world. Architects designed a sleek glider-shaped terminal, its main atrium a soaring 30 meters high, connecting to a uniquely curved wing-shaped departure concourse that measures a staggering 1.7 kilometers.
I think Kansai International Airport, this shape and space is unique. Kansai is huge, but you feel very human scales.
But the real design challenge was how to create a building that would not fail when attacked by the forces of nature.
We must be very, very careful this natural strong force.
Kansai Airport in Osaka Bay, a hub of futuristic design. This wing-shaped terminal, when built, was the longest building in the world. It has 41 gates, handles millions of passengers a year, and is Japan's first 24-hour airport. But building an airport terminal in an area prone to violent earthquakes presented architects with some near impossible design challenges.
Of course, in Japan, we have many strong earthquakes. Engineering point of view, architecture point of view, we must be very, very careful. This natural strong force, we must consider all of them. That is very, very important challenge.
To prevent the building suffering from a catastrophic failure, engineers had to design a system that would withstand huge force.
Building design is that. We have many mechanical systems for the joint absorbing earthquakes.
The key solution was to make sure that every part of the building could move independently.
This bridge must be flexible. So when earthquake attack, this handrail is moving like that, absorbs the movement. This wall is moving like that, absorbs the movement. Floor is moving like that, absorbs the movement.
As well as movement-absorbing joints, engineers needed an additional system to construct the 4,000 square meter glass walls.
This is window, huge windows. It takes some movement of the earthquakes. We use for the gasket system. If the movement coming, it's absorbed with rubbers, better than another system.
Glass cannot dissipate energy as it's too brittle. The rubber gasket around each pane absorbs any seismic energy and allows each one to move individually. In all, 5,000 glass panels were installed. The terminal was constructed over a period of 3 years by over 10,000 designers, engineers, and workers from across the globe. But soon after completion, the airport design faced the ultimate challenge.
1 month after the opening, a typhoon attacked this Kansai International Airport. And 4 months later, we had Kobe earthquakes. So we were tested.
In January 1995, Kobe earthquake struck the Osaka Bay region, killing more than 6,500 people and damaging over 150,000 buildings. But Kansai Airport passed the test, and not so much as a single pane of glass was broken. Since then, Kansai International has seen nearly 2.5 million flights, carrying 300 million passengers. But a century earlier, this incredible 24-hour stream of incoming and outgoing aircraft would have been totally impossible. The roots of civil aviation began after the First World War. Passenger planes were for the daring few, often converted bombers flown by ex-military pilots. Scientist Andrew Steele is getting a taste of flying from the days when rules were few and only the brave took to the air.
Would you go for a gentle loop-the-loop?
Yeah.
Pop the nose down, increase the speed to 100 knots. Now look up. That's it. All the way up. All the way up. All the way over.
Oh, and the whole planet is upside down. That was amazing.
And back to
wow.
It's unthinkable today, but in the days before air traffic control, flying was largely unregulated. Pilots had to rely solely on what they could see to avoid mid-air collisions.
There's another aeroplane. So we just had a Cessna fly past our right wing, and the only way that I know that is because the pilot was kind of pointed out for me. There's no radar or other instruments in the plane that allow us to know where other planes are in the sky.
Pilots also relied on the most basic of navigation.
For me, the only way that I can tell where I am is by looking at the ground underneath me and comparing that to a map.
After the First World War, landing strips used by fighter planes became designated flying sites, or airports. And by the early 1920s, Croydon Airport near London was the busiest in the world. But as traffic intensified, it was clear that if chaos in the skies was to be averted, a new solution would be needed. It was Croydon's chief radio operator, Jimmy Jeffs, who, using the plane's ability to transmit a simple signal, invented a system that we now recognise as the first air traffic control.
The system they came up with was called triangulation, and it works like this. Imagine there's a plane over there, and I want to know exactly where it is. Now, I can get that plane to start broadcasting a radio signal. I can then look around and find out the direction in which that signal is strongest. And then I know that the plane is somewhere along that line. In order to work out exactly where it is, though, I'm going to need to go upstairs.
The radio operators tracked the plane's signals from a tower, which gave them a bird's-eye view of the airfield.
So this is where the radio operator would have sat, wearing some headphones like this, and he'd have listened out for the bearing the plane was coming in on, the strongest direction of that radio signal. So if you listen carefully, there we go. I think the bearing is about 185 degrees. So it's time to move over to the triangulation chart. We're here in Croydon, and the bearing that I got was 185 degrees. And now we know the plane is somewhere along that line, but we don't know where. The great innovation from here in Croydon was to realise that we could ask another radio receiving station that also had a directional aerial. So we might try this one in Lim. And these guys reported a bearing of 254 degrees. So let me just, there we go, line that up. Now, using these two bearings, you can see where they cross, X marks the spot, that's where the plane is. And if we want to be doubly sure, we could ask a third radio receiving station. So these guys up here in Fulham, they report a bearing of 206 degrees. So that third bearing from Fulham confirms what we thought, the plane is definitely over Brighton. So we can move over to the plotting chart, grab a pin, and there we go, position our incoming aircraft. And now not only do we know where that aircraft is, but we've got the positions of all the other aircraft too, so we can make sure they're not going to crash into each other.
Thanks to this innovation, pilots knew where they were and could find destinations, making scheduled flights a reality. In 1922, Jeffs was issued with Air Traffic Control Licence number 1 and became the world's first air traffic controller. Controllers at Kansai still rely on the same basic principles to keep track of planes in its airspace. Today, the system also displays aircraft identification numbers and records of speed and altitude. As well as ground-based receivers for triangulation, the signals are now detected by a network of satellites called a global positioning system. This cutting-edge technology allows planes to take off and land every 4 minutes, 24 hours a day. But to keep the airport running and catastrophe at bay, Kansai would need to employ one more piece of impossible engineering.
This place is a sort of hidden place. Only the few people know this system.
Kansai Airport in Osaka Bay, Japan. The first airport built on its own specially created island. This unique single structure, welcoming millions of passengers each year, connecting to 25 countries, is one of Japan's leading air terminals. Engineers overcame extraordinary challenges to create a cutting-edge building capable of withstanding powerful seismic forces.
We had a very good team, both engineer team. I think Kansai is one of the unique buildings still.
But Kansai would need to produce more impossible engineering. After stabilizing the seabed, the island was predicted to sink by up to 6 meters. But after 3 years, it had already sunk by over 8 meters and was still going down. And it soon became clear parts of the island were settling at different rates, putting unequal stress on the terminal structure.
Such an even settlement may cause some cracks of the buildings or some disconnections of the cables or the pipe or like that.
If too much strain was placed on one section of the building, it could subside. To hold the terminal's enormous weight and save it from collapse, engineers would need to turn to a groundbreaking innovation from the past. Humans have always had great ambition to build big. But to lift huge weight, muscle power was not enough. The ancient Greeks built the first crane using a simple pulley. Lots of power generated by just a few men. But it was hard to control. Leonardo da Vinci invented the screw jack that could lift weight from below, transferring rotary motion to linear. But this still relied on human strength. Finally, in the 19th century, tired New York mechanic Richard Dudgeon had an idea. He boosted human power with hydraulic power. His new jack compressed oil from a narrow cylinder into a wider one. The pressure in the second cylinder was equal to the first multiplied by its size, therefore lifting more weight. Engineers at Kansai have taken this innovation and used it in a remarkable way.
This place is a sort of hidden place. Only the few people know this system.
A system that thousands of daily passengers above are completely unaware of.
This is the jack-up system, and then this is the hydraulic jack.
In the basement of the terminal building, 900 fully automated individual hydraulic jacks have been installed to counteract any uneven settlement. Sensors in a control room detect when one part of the building is out of kilter with the rest. Each jack, capable of lifting 300 tons, can be activated individually. Steel wedges are used to support the building at the new height.
You can see many steel plates. The thickness is about 10 or 15 centimeters.
The technique is repeated until the terminal is level. Without this innovation, the whole building would have failed.
If this system is not here, then the ground settlement may cause very severe damage to the building itself.
Engineers at Kansai have employed many unique systems of engineering to adapt to the island's environment. The single terminal building is a design masterpiece. But there is one system, the stacking of departures directly above the arrival floor, which is key to the building's success.
I think if you imagine for the domestic, international separately, we need more space in the surface. This sandwich system, this is the first time in the international airport system in the world.
But with hundreds of flights a day, carrying up to 50,000 passengers with thousands of items of luggage, the challenge of moving bags between floors, security checking and delivering them to the right place on time, in a building nearly 2 kilometers long, posed a very specific conundrum.
I think baggage handling is so important in the airport terminal building and not easy.
The solution owes an enormous debt to the key innovators of the world's industrial past. The Industrial Revolution was a pivotal moment in history. It marked the transition from manpower to machine power. Whilst it was the steam engine that provided that crucial power, key to driving the revolution forward was the conveyor belt. Professor Andrew Steele is finding out why.
The basic principle behind a conveyor belt is actually very simple. What you need is a series of rollers and then stretch a belt around those rollers. By turning the roller, the material then moves. For example, if I place an object on this end of the conveyor belt and then provide power to the drive pulley, use this rotational power that I might get out of a steam engine, for example, to move the object linearly along the belt.
Conveyors were initially flat, made of wooden rollers and belts of cloth, which restricted durability and capacity. However, in 1891, American industrialist Thomas Robbins realized their potential. His contribution was to supercharge the industrial world.
Firstly, he took the flimsy material of the belt and coated it in rubber, which made the belt itself a lot tougher. And secondly, he developed this three-point roller system, which curves the belt into a U shape and stops the rocks from falling off.
Robbins' robust conveyors could now carry hard, heavy substances, and when applied below ground, transformed the coal mining industry, fueling manufacturing around the world. Robbins' development of the conveyor belt paved the way for its adaptation across the industrial spectrum. Modern manufacturing now uses a variety of fully automated conveyor assembly lines with innovative features of their own.
One of the key differences between these modern conveyor belts and the more simple original versions is that these can go round corners. And the way that works is that rather than being a belt of material, they're actually made up of a series of interlinked bits of metal, which allows it to articulate in different directions.
Thanks to the innovators of the past, advanced conveyor belt systems are now integral to our everyday life, from manufacturing to mining and even restaurants. At Kansai Airport, designers have incorporated many cutting-edge innovations into their luggage conveyor belt system and created something special. The unique challenge within the compact terminal was to get baggage from international check-in on the top floor to the aircraft 14 meters below.
We can't make this sort of a system because we have no space to do that.
What the designers came up with was the tallest spiral baggage conveyor system in the world, measuring 700 meters in total, that transports over 10,000 items of luggage each day.
I think its spiral system is a very good choice.
But crucial to efficiency is the tracking system. Each bag is barcoded and special sensors track its progress along the conveyor. When it reaches the correct floor, a 3D tilt tray is activated, releasing the bag, so that 3.5 million items reach their correct destination each year.
This airport works well, and I think I'm very proud of that.
It took 20 years from conception through construction to raise an entire island from the depths of Osaka Bay and create a leading international airport capable of withstanding nature's most violent attacks. But by drawing on the innovations of the past, adapting, improving them, and making groundbreaking innovations of their own, the engineers, designers, and workers on the Kansai Airport overcame extraordinary obstacles and succeeded in making the impossible possible.
Kansai Airport Island was the biggest man-made island in the world. Every engineers and every people involved in this project believes that we achieved the impossible.
The fastest passenger train on the planet.
It's flying pretty much at 431 kilometers an hour.
Seemingly defying the very laws of nature.
The train floats at 1 centimeter from the guideway.
And the pioneering historic innovations.
Wow, it looks like something out of the future.
I don't think without the L we would have had this great, vibrant American city that we have today.
That made the impossible possible. China is a country on the rise, and it's aiming for the stratosphere. Shanghai is a global and financial hub, which attracts people from all over the world with its ambition. As the influx of people increases, so too does demand for space. The city faces heavy traffic jams and congestion on a daily basis.
Shanghai is busy. Cars as well as buildings fight for space on the ground. It can be very difficult to move around.
By the beginning of the 21st century, Shanghai faced a seemingly impossible engineering challenge. An increasingly congested 8-lane highway was Shanghai's only link to the important Pudong International Airport. And traffic was getting worse.
To get to the airport by car, it takes 45 minutes to travel just 40 kilometers. You really need something to cut through the city to get to the airport without stopping and without encountering any other vehicles. I, like most people in this city, don't have time to sit in traffic.
The solution would be the Shanghai Maglev, or Transrapid. A futuristic concept currently unique in the world.
The thing that's different and very unique about the Maglev is the fact that it floats. It hasn't got any wheels, it floats across the guideway all the way to the airport. Now the Maglev is just about to pull out of the station. When it's at its top speed, it'd be moving at 431 kilometers an hour. That is just beyond belief, incredible.
In order to create this modern marvel, the designers and engineers of the Maglev would have to overcome several apparently impossible challenges. The Maglev's creators were planning to throw away several of the key historic engineering innovations that are the mainstay of current train travel. First, the train would be engineless. And it would do away with one of engineering's most fundamental inventions. Not only that, it would seemingly challenge the most basic of principles. But for the designers of the Shanghai Maglev, the problems begin before they can even conceive the train. How to fit a brand new transport system into an already busy and growing city.
Shanghai is one of the most heavily populated cities in the world, and the population is increasing. Now, building the infrastructure it needs is very challenging just because there is no space. Like all the buildings around here, the only place really to build is to go up.
Chicago is one of the world's busiest modern metropolises. The logistical challenge of moving its inhabitants is huge. Yet, thanks to the work of some of the city's pioneering engineers, the solution they implemented well over 100 years ago is still in use today.
In the late 19th century, Chicago is one of the fastest growing cities, if not the fastest growing city in the world. In the 1840s, shortly after the city was established, we had roughly about 4,000 people. And by 1900, we've got over 1.5 million. Our city is rapidly expanding. It's almost the Shanghai of the late 19th century.
So how could engineers and planners deal with the seemingly impossible challenge of transporting a growing population without clogging the already busy city streets further?
So this is the solution that was developed to elevate the city's rail lines above the street traffic. Although it's not cheap to do this type of infrastructure, it is cheaper, of course, than building subways.
Work began in 1892. But building a railway 30 feet above established city streets required a massive engineering effort and was at first not welcomed by everybody. Third-floor apartment dwellers now had to keep their curtains drawn if they wanted privacy. And young women were warned to be careful of roving rail-borne peeping toms. Nevertheless, for the masses, the system was a big hit. It was lovingly nicknamed the L, short for elevated.
We're here at Quincy. This L station has been restored, and it gives us a sense of what commuters would have seen in the late 1890s. And the basic concept of moving people in and out of the city at a different level than street level has not changed since then.
Elevating the city's railways was a solution so successful that more than 120 years later, it's still transporting around 500,000 passengers every single weekday.
The growth of the L and the growth of Chicago are synonymous. The boom of population in the late 18th century follows right along with the growth of this transit system. And I don't think without the L we would have had this great, vibrant American city that we have today.
Engineers in Shanghai have taken the Chicago solution of an elevated railway and created a 30-kilometer-long guideway soaring above Shanghai's streets.
The advantage a system like this has in already built-up urban spaces is it's very easy to install. It doesn't interfere with underground services. It doesn't interfere with existing infrastructure at ground level, which is really good.
But building an elevated railway in Shanghai means overcoming a very specific, potentially catastrophic danger.
Shanghai sits in an area of great seismic activity. It also has weak clay soil. The risk of liquefaction is very high.
Liquefaction is an unusual and dramatic effect that can occur during earthquakes, when seemingly solid ground mysteriously turns to mush. Physicist Andrew Steele has prepared a simple demonstration to show just how liquefaction works.
So this water represents the groundwater. This ground has got a very high water table, so it's only got a thin layer of dry soil on top of the saturated soil underneath. So imagine you build on this land. You construct your beautiful city. But you built on sandy soil and you built on a fault line, so there's the danger of an earthquake. You can see that as you shake it, then the groundwater is forced up into the top layer of the soil, and that changes its state from that of a solid to very much behaving like a liquid. And the buildings are just sinking straight into it.
With earthquakes a constant threat in Shanghai, measures would need to be taken to make sure the Maglev didn't sink into the soft ground the next time one hit.
Engineers came up with a technique called piling. Each support pier was built on top of concrete cap, about 2 meters deep and approximately 12 meters wide. Underneath the cap are 20 to 24 concrete piles that were driven to depths of a staggering 70 meters.
The concrete caps provide a solid base, which is supported by the multiple piles. So, if the soil near the surface liquefies, the deep roots will hold the Maglev guideway firm. In double-quick time, Chinese engineers constructed over 2,500 concrete columns to support the guideway.
It took less than 9 months to sink foundation piers every 25 meters along the entire 30-kilometer route.
However, engineers had further challenges to face, and they'd have to turn to the great innovators of the past.
Ooh, that was fast.
To produce more impossible engineering. The Shanghai Maglev is the fastest passenger train on the planet. A vision of the future that literally flies along the ground at a staggering top operating speed of 431 kilometers per hour. This piece of impossible engineering has transformed travel between Shanghai's airport and the busy cutting-edge metropolis.
The Maglev runs all the way from here to Pudong Airport, which is a 34-kilometer journey in that direction. Now, if I was to get the metro, it would take me over an hour. If I got a cab, it would take me 40 minutes or so. But if I got the Maglev, which I like to do, it takes me only 7 minutes.
Creating a train this fast presented engineers with major challenges.
This would be the fastest train in the world. But trying to get a train up to speeds pushing 500 kilometers an hour, designers would be faced with the problem of wind resistance or drag. The greater the speed, the greater the resistance, and all this air movement has the potential effect of slowing the train down and wasting valuable energy.
The earliest evidence of primitive railways can be traced back to ancient Greece, where men and animals pulled wheeled vehicles that ran in limestone grooves, thus preventing the wagons from leaving their intended route. Railed transport was devised as a way of reducing friction. In England in 1805, it was demonstrated that a good horse on an ordinary road could pull a wagon weighing a ton. But on rails, it could pull a train of 12 wagons, each weighing 3 tons with ease for 6 miles in 2 hours. Add steam power, and whole continents could be crossed with ease, transforming the modern world. Despite the railways dramatically changing the way we live, by the 1930s, aerodynamic design had stood surprisingly still.
Train design fundamentally hadn't changed for 100 years since this, Stephenson's rocket. You can see the classic cylindrical boiler, we've got the smokestack at the front, and this completely snub, flat, unaerodynamic nose.
It would take a radical thinker to come up with a plan that would change train design forever. In the north of England, steam locomotive engineer Nigel Gresley produced a new, sleek machine that would be the fastest train in the world. The Mallard.
Everything about this locomotive is designed to go as fast as possible. You've got these massive wheels driving it forward. We've got a double chimney to suck out the exhaust as quickly as possible at high speed. And then you've got this beautiful streamlined shape, in stark contrast to the trains that had come before.
In order to create his design, Gresley used a wind tunnel, previously the preserve of aviation, and found some interesting results. Andrew Steele is visiting test centre The Train Rig in Derby to see what a difference a streamlined design can create.
This is the test track. It's 150 metres long, and we can accelerate trains to 75 metres a second, which is over 250 kilometres an hour. Today we've got two different trains that we're going to be testing. This is a flat-nosed freight train, which represents sort of an unaerodynamic train as they were originally designed. And this one here is a high-speed train, got this sloped nose. We're going to see what difference that makes to the speed the train can travel at. And this is what we're going to be using for the actual experiment. These things here are light gates, and when the train goes past this one, it interrupts the light beam, and we can detect that time. Then a fraction of a second later, it'll go past this light gate, interrupts this beam, and by measuring the difference between those two times, you know this distance here, so we can work out exactly how fast it's going.
The model trains are fired using giant rubber catapults.
So we're just applying some tension to the track now, and that's pulling the train back into the firing position. I'm almost as tense as the train is. Okay, so just, here he goes. Ooh. That was fast. Ooh. And believe it or not, that was a sort of slow test run. So now we've done that test run, the key thing is to find out the readings that we got from these light meters. We've got two readings here. At the first set of light gates, it was doing about 36 meters per second, but then by the time the second set of light gates, just a couple of meters later, it's only doing 34.5 meters a second. So you can see it's lost some speed, the aerodynamic drag has kicked in and slowed the train down.
In the short distance between gates, the flat-nosed train loses around 5% of its speed. Next to be tested is the sloping-nosed model.
Ready, aim, and fire. Wow.
This time, the model speed reduces by only 2% between the light gates.
So these numbers, they're quite subtly different, but when you scale it up to a full-size train and you're looking to propel it constantly down the track, this can translate into a big change of efficiency.
A fact Nigel Gresley spotted and exploited brilliantly.
Gresley's engineering really was a complete step change. Although we'd used aerodynamics in planes and hydrodynamics was known about in boats, this was the first time those principles had been applied to a train. And that's what enabled a Mallard to travel at 126 miles per hour.
In 1938, the Mallard set the record for the fastest steam train on rails, a record which still stands today. Designers of the Shanghai Maglev have learned from the breakthroughs made by the Mallard and created a train that travels at speeds that innovator Nigel Gresley would have thought impossible. In one test run, it exceeded 500 kilometers per hour. Way over twice what the aerodynamic Mallard was capable of.
You can see it has a very sleek, streamlined design with the very smooth, sloping nose. Also, the train wraps itself around the guideway, which reduces turbulence that might otherwise be generated between the train and the track.
But the development of the futuristic Maglev system took decades of experimentation before it reached its incredible 21st century performance levels. Created in Germany, the first passenger-carrying prototype, the Transrapid Maglev system, was unveiled in 1971. At that time, travelling at speeds where little consideration to aerodynamics was necessary. However, as experiments continued and velocities rapidly increased, the carriage design that now graces Shanghai's elevated track quickly took shape. But with increased speed comes additional engineering challenges.
the maglev going to the airport and the maglev coming from the airport pass each other at incredible speeds, potentially a combined speed of over 860 kilometers per hour. And this could cause a potential problem. However sleek the design, any object passing another at speed creates a change in pressure between them. Lower pressure as the trains are together, followed by a return to a higher pressure once they've passed. This could potentially cause stresses to the cabin walls. So maglevs have been engineered with an aluminium composite shell, light but at the same time strong and stiff enough to support the pressure acting on the structure by high-speed traveling.
To take the Transrapid system to record-breaking speeds, engineers could draw inspiration from a trailblazer of the past.
They combined the principle of the hovercraft and a jet engine, and they smashed the rail speed record.
To create their own impossible engineering. The Shanghai Maglev, the world's fastest passenger train. A unique engineering feat situated in one of China's most ambitious cities.
This maglev here is the only high-speed maglev in the world, and that kind of chimes in with the ambition of Shanghai. People come here to be able to design daring buildings and daring systems.
And one of the most daring of them all is the maglev. Travelling at a staggering 431 kilometers per hour and seemingly defying nature. But to create this space-age transit system, its engineers would have to conquer some seemingly impossible challenges.
It's not just the wind that provides friction on the train. One of the biggest losses of energy that occurs in a traditional train is produced by the friction between the wheels and the track. The more friction there is, the more power is lost. In a car like this, for example, 1/3 of the fuel is spent on overcoming friction.
To enable it to reach its record-breaking speeds, the maglev's designers would have to overcome a challenge that only history's most daring engineers have achieved. In the French countryside, physicist Andrew Steele is looking for the remains of a system that could have been every bit as revolutionary as the maglev.
So here it is, over 50 years old and covered in moss. This is what its creators thought would be the future of high-speed mass transit. A single concrete rail straddled by a train capable of travelling at 422 kilometres an hour, at a time when the speed record for a conventional train was just half that.
So what kind of vehicle was capable of overcoming the forces of friction to travel so fast? The answer lies in a closely guarded warehouse.
I've come to a top-secret location somewhere outside Paris to get a rare look at what could have been the future of land transportation.
Hello.
Good morning. So, where's it kept?
Hidden amongst an assortment of military vehicles collected by Thierry Farge are the last surviving examples of an extraordinary experiment.
Wow. So this is the aerotrain?
Yes.
It looks like something out of the future.
Designed by engineer Jean Bertin in the 1960s, The Aerotrain 1 and 2 are the only surviving prototypes for a system it was hoped would change travel forever.
You can see the Aerotrain doesn't have any wheels. Now, that might seem strange, but although wheels have been the basis for land transport for thousands of years, they come with a big disadvantage because the wheels rub against the ground, they create friction, and the Aerotrain tries to get round that.
Engineers and scientists have been toying with the idea of frictionless travel for some time. The idea is that if you can remove that frictional resistance to motion, then you can make things travel faster and more efficiently. The simplest way to do that might be to levitate it on a cushion of air, and that's the principle behind how a hovercraft works. We've got our own very simple model of a hovercraft here. It's just a CD with the top of a drinks bottle on it, and then a balloon. Before we inject that cushion of air, the CD only moves a very small distance across the table when I tap it. However, what we can do is attach a balloon to this drinks bottle top and see if that makes any difference to the way that the CD moves. So, there we go. You can see that now, with a tiny tap, the CD moves a long way. And just as long as the balloon's got some pressure to force that air down underneath the CD, then it'll keep on moving around freely. But when the balloon runs out, of course, the cushion of air vanishes and the CD is just as hard to move across the table as it was before. In here, we've got the guts of the Aerotrain. And incredibly, there are just two regular car engines which power massive fans, and that blasts air downwards to lift the train up off the ground, and then inwards to keep it centred on the track. That means that the train isn't in contact with the ground or the track, and so that source of friction is removed, and that means that more of the energy from this engine up here, the propeller, can be used to power the train to move forwards. It's 11 metres long, weighs 2.6 tonnes, and yet the air gushing out of these nozzles was enough to keep it floating 2 or 3 millimetres above the track.
By 1967, the Aerotrain was already proving its potential on the test track as a new form of speedy passenger transport.
It planned to build a track for the Aerotrain between Paris and Orly, 65 miles in 35 minutes. Vive la sport!
But for Aerotrain Mark II, Bertin went all out for speed. The Aerotrain 2 was a futuristic hybrid of jet fighter, racing car, train, and hovercraft. And although it looked like something out of a sci-fi movie, the technology itself was fairly basic.
I think my favourite control is this one that goes marche and arrête, so it's basically stop and go just by flicking a switch.
Nevertheless, it was the combination of engineering ideas that made Jean Bertin's Aerotrain groundbreaking.
Bertin's ideas really were revolutionary. They combined the principle of the hovercraft and a jet engine, and this was the first time it had ever been done. Combined, they smashed the rail speed record.
An aircraft jet engine gives initial thrust up to speeds of around 185 miles per hour. An additional rocket motor boosts the MPH to 235.
Sadly, Jean Bertin's dream of friction-free travel died in the 1970s when the French government abandoned the experiments. However, the Aerotrain now has a familiar-looking cousin, over 6,000 kilometers away in China.
I traveled in the Maglev, we hit 400 and I thought, oh my goodness. And then it continued to travel even faster. I could not believe what I was seeing and experiencing. And it's currently doing a top speed, flying pretty much at 431 kilometers an hour. And it still feels very comfortable for the speed at which it's traveling. The Maglev is faster than the Formula One car. It is flying along.
This record-breaking feat is possible because the Transrapid Maglev is not a hovercraft, like the French Aerotrain, but is instead flying above the track, levitated by powerful electromagnets. A piece of engineering magic that would have been impossible without one of science's great innovators. Born in 1791, the son of a blacksmith, Michael Faraday received little formal education, but would go on to revolutionize the world. His original laboratory still exists at London's Royal Institution.
If I give it a little push.
Where physicist Andrew Steele is exploring how Faraday's discoveries made magnetic levitation possible.
Faraday's discoveries revolutionised our understanding of the interplay between electricity and magnetism. And one of the things that this understanding allows us to make is an electromagnet. So an electromagnet is made of a coil of wire. You then need to get the ends of those pieces of wire and plug them into a power supply. And finally, to magnify the magnetic effect, you often place a core of a material like iron in the middle of the magnet. Let's connect this up. And to prove to you that that's magnetic, you can see that even with this extremely simple setup, we can actually get a piece of metal to stick to it. Another crucial fact about electromagnets, if you want to use them for levitation, is that we can change their strength, and we can do that very easily. Just by changing the electric current passing through this magnet, I can turn the current down and make the attraction much weaker, or I can turn the current up and make that attraction get stronger again.
Not only can electromagnets be adjusted or turned on or off at will, but they can also be significantly stronger than ordinary magnets.
If you want to suspend an entire train, you're going to need a pretty powerful electromagnet. And actually, electromagnets are pretty strong. This little one is enough to suspend my entire body weight. And actually, this thing needs surprisingly little electric current. There's less electricity flowing through this device than there is through your hairdryer or your kettle at home. We've got an electrical current flowing through this electromagnet. If we connect it to the piece of metal on my back, then hopefully there should be enough strength to hold me above the floor. And there you have it.
On the Shanghai Maglev, banks of powerful electromagnets are installed into units that sit on the underside of the carriages. Guidance magnets keep the train centred, and support magnets attract the unit to the underside of the track, and so lift the train above. The entire train therefore effectively flies, suspended 10 millimeters below the track. Not only does this make for extremely fast, friction-free travel, but also reduces wear and tear.
Because there's no contact between the train and the guideway, there is no friction, and this means that the train can have a lifetime of up to 50 years with minimum maintenance required.
But to create a train fit for the future, its designers would still have to look to one of history's greatest innovators.
When I put it on the motor and switch on the magnets, something pretty dramatic occurs.
To create yet more impossible engineering. Travelling at an astonishing 431 kilometers per hour, whilst floating on a magnetic field. The Shanghai Maglev is the only high-speed train of its kind operating commercially in the world. But to create this wonder of modern engineering, its German developers would need to overcome some seemingly impossible engineering challenges. Including creating a propulsion system in tune with its futuristic home.
China, like all modern economies, is worried about its carbon emission quota. As development continues, the demand for oil will also likely increase. But China has a limited domestic oil supply. With its current gas-guzzling congestion problems, greener transport initiatives are drastically needed. Otherwise, the city will choke.
The solution would have been impossible without one of history's great engineering innovators. In the late 1940s, one British engineer's experiments would ultimately earn him the nickname, the father of maglev.
This is a sheet of aluminium. When I put it on the motor and switch on the magnets, something pretty dramatic occurs.
Electrical genius Eric Laithwaite developed the first practical linear electric motor, creating an effect he later dubbed the magnetic river.
First of all, it will levitate or support an aluminium plate. It will guide it sideways, and it will also propel it along.
The linear motor essentially takes a traditional coiled electric motor and unrolls it. Instead of spinning a rotor, what was the coil or stator provides a bed that drives the object along its length.
And there you have your modern vehicle being guided, lifted, and propelled, all by means of the same set of coils.
Laithwaite's experiments provided the key that unlocked the potential of the maglev. The German builders of the Transrapid maglev system constructed a series of stator blocks that are the main component of the linear motor and act as the propulsion system for the train. Once installed, they were tested in Germany, and in combination with the support and guidance magnets, enabled this unique vehicle to levitate. Relocated to Shanghai, the maglev vehicle travels at well in excess of 400 kilometers an hour without an onboard engine.
A linear motor is embedded into the guideway for its full 30 kilometers. But don't be fooled into thinking this whole track is electrified all the time. What is so brilliant about this system is that only the sections of the track on which the vehicle moves is powered at any time. So as it sets off, the 30 kilometers of track ahead of it is dormant, and only the section in front of the maglev turns on. As soon as the maglev has passed over the short section of track, it turns off again, as the job of pushing the maglev along is taken up by the next section of track, and so on, all the way to its destination.
Having a levitated train traveling at such speed creates several unique engineering challenges.
There's a carriage hurtling along at over 430 kilometers per hour. So it is critical to control fluctuations in the magnetic field and maintain an even gap between the train and the track, no matter how many passengers are on board or what variations there are in the load it's carrying.
With a mere 15 centimeters between carriage and guideway, any errors could see the train crunch into the track. The solution, as physicist Andrew Steele demonstrates, relies on sensors constantly regulating the current in the electromagnets.
There we go. You can see this permanent magnet is suspended underneath this electromagnet. Whenever the permanent magnet moves slightly imperceptibly closer, this little sensor on the bottom here detects that, sends a message down to these electronics, and tells the electromagnet to become a little bit weaker. It turns down the current. And that allows the ball to fall away a little bit. And as it falls away, the sensor detects that again and increases the strength of the electromagnet and pulls the ball back towards it. So one complication of this system is that your feedback system always needs to be working, and it needs to be working very fast. You can see this ball is spinning and wobbling a tiny bit, and that's fine for a little demonstration like this, but if you've got a train travelling at hundreds of kilometres an hour along the track, you're going to need a very, very sensitive and accurate feedback system.
the Shanghai Maglev takes this simple concept to a whole new level. There are 128 sensors in every section of the Maglev vehicle. They feed back the distance between magnets and guideway thousands of times a second, allowing powerful computers to adjust the electromagnet's current constantly and with microscopic accuracy.
This is the guideway, and the train floats 1 centimeter from the guideway. Now that is incredible precision. Now there's a computer system that makes sure that all of the time the train floats at 1 centimeter from the guideway.
The advanced computer system also regulates the running of the whole service, meaning each journey time is predictable to the second.
Now this is the ambition of the Maglev. With computer systems, they've been able to achieve an extremely precise service.
It's taken decades of planning, design and testing to create the world's only commercially operating high-speed maglev. A unique concept that throws away the rulebook for traditional train travel and makes high-speed journeys possible in engineless vehicles.
A system like the Maglev points to the future of transport in our world. Incredible things to be achieved. This shows us that we can get people moving from A to B in short periods of time, which is great.
By drawing on the innovations of the past, adapting, improving them, and making breakthroughs of their own, the designers and engineers of the Maglev have realized the dream of a superfast train that flies without wings, and succeeded in making the impossible possible.
It's kind of unbelievable that there's a train that goes over 400 kilometers an hour. It is a vision of the future, and it's here right now.
The biggest passenger plane the world has ever seen.
When you see that huge monster, impossible that this big thing is gonna fly. No way.
It's cutting-edge aerospace engineering.
A massive fly-by-wire system like this is an incredible tool of safety for the aircraft itself.
And the pioneering historic innovations.
What an incredible sensation!
Cayley was the first person to recognize the important forces that are fundamental to understanding flight.
That made the impossible possible. Since the birth of aviation a century ago, air travel has reached monumental proportions. Now, over 3 billion passenger journeys are taken each year. That's the equivalent of half the world's population taking to the skies. With terminals overrun and runways congested to breaking point, aerospace engineers are looking for solutions.
15, 20, 30 years ago, the challenge in the aeronautical field was mainly speed. Then the new objective of Airbus, Boeing, for example, was the size of the aircraft.
In order to reduce the 100,000 daily flights across the globe, aircraft designers would need to think big. And in 2007, what they came up with would smash aviation records. This is an Airbus A380, an ultra-high-capacity airliner and the largest passenger plane on the planet. An aircraft so big that Air France have had to create a giant cutting-edge building just to accommodate it.
We built that brand new hangar to welcome that huge monster, that huge aircraft, so big that our hangars couldn't fit that kind of aircraft.
This revolutionary double-decker plane has an almost 80-meter wingspan, the largest of any commercial aircraft. It has 550 square meters of usable floor space, a massive 40% more than the next largest airliner, allowing it to carry up to 850 passengers. And its mighty turbofan engines and state-of-the-art design mean it can fly non-stop, almost halfway around the planet. At its custom-built high-tech hangar in Paris, this Airbus is being stripped back as part of its scheduled 4-year service, revealing the secrets of its engineering success. And for maintenance manager Sylvain Fargo, it never fails to impress.
The first time when I see it, the first word was wow, and it's still wow when I see it. This aircraft was part of what we could call a jump in the aeronautic industry. New technologies required from us to train our mechanics, our engineers, so it's quite a step through future.
The A380 is a colossal feat of engineering that would have once been thought impossible. Man has always dreamt of flying like a bird. But liftoff was not as easy as it looked. 11th century Benedictine monk Almar reportedly strapped wings to his back and launched himself off Malmesbury Abbey. But he glided out of control to come to a painful landing. In 18th century Paris, the Montgolfier brothers, noticing that hot air made a paper bag rise, built a hot air balloon and made history with the first ever lighter-than-air manned flight.
Oh, très bien, magnifique.
Although their design did have its drawbacks. But for a flying machine heavier than air to take off and remain airborne, engineers would have to learn how to harness the forces of nature. This would remain an impossible dream. Until, in 1804, British scientist Sir George Cayley closely observed birds and finally unlocked the mystery of flight, earning him the title, the Father of Aeronautics. Cayley discovered that in flight, a bird's wing has a curved shape known as an aerofoil. Air passing over the curved surface speeds up, losing pressure. The pressure of the undisturbed air below remains high, and so creates upward force. Cayley built a whirling arm to test his theories. By turning the aerofoil upside down, aerospace engineer Dr. Ben Evans can demonstrate how this shape can successfully conquer the forces of gravity.
Now, in this experiment, on one side we've got weights representing gravity, the force that needs to be overcome, and on the other end, an aerofoil. And as this spins, the arm goes level. The air passes over the aerofoil and pulls it down to counteract gravity, which is what lift is trying to do in an aircraft, only upside down.
In 1853, at the age of 79, Cayley put these ideas into practice and launched the world's first heavier-than-air manned glider. Sir George Cayley had made the impossible possible.
It's amazing what you get it to do when you know how.
Cayley's achievements have inspired generations of aerospace engineers to reach for the skies.
By doing some very simple experiments, he managed to show what allows a wing to generate lift, just like the wing of this glider that is allowing us to hang here in the skies.
Without the concepts that George Cayley developed, the giant engineering feat of the Airbus A380 would not be possible.
When you see this aircraft, it's so huge, you can say, but impossible that this big thing is gonna fly. No way. But in fact, it's only aerodynamics.
The A380's wings apply the same principles that Cayley exploited, but on an enormous scale. With an almost 80-metre span and a surface area of 845 square metres, they're big enough to park 20 of Cayley's gliders on top. In its custom-built hangar in Paris, this A380 is in for a comprehensive service, allowing technician Charlie Jackson to get up close and personal with these engineering masterpieces.
As this aircraft is taking off down the runway and generating speed, the tips of the wings actually will raise up about 4 meters, which is a sign that the wing is generating the lift that it's going to need to carry such a large aircraft into flight.
To create a wing big enough to generate lift but small enough to minimize drag is a design conundrum. On the A380, special high-lift devices, slats on the front and flaps on the back, allow the wing to increase its size and curve depending on how much lift is required. The wings also maintain the plane's aerodynamic qualities in a more surprising way.
The inside of these wings is the fuel, which you need to complete your flight.
The plane has 11 fuel tanks, 5 in each wing and 1 in the tail. Fuel is stored in the inner tanks to reduce weight at the wingtips. After takeoff, it's pumped to tanks across the whole wing. Throughout flight, the system constantly adjusts the fuel to maintain the center of gravity.
This wing is the product of good design. If it hadn't been that way, it just wouldn't be practical to make an aircraft that size.
But to create a super jumbo, unlike any other plane in the skies, its designers and engineers would face further major challenges and have to draw on innovations from the past.
What an incredible sensation! I can feel the acceleration pushing me back into my seat.
To produce more impossible engineering. The Airbus A380 is a triumph of 21st century aerospace engineering. The largest commercial airliner in operation today. At its state-of-the-art, custom-built hangar in Paris, this A380 is undergoing its 4-yearly service, allowing admiring technicians to get intimate with this colossal feat of impossible engineering.
It's a big aircraft. You cannot imagine that it's gonna go and fly so easily.
But designing a huge plane created huge challenges. Not least how to create engines powerful enough to lift a 369-ton aircraft plus 200 tons of passengers, fuel and cargo, almost 4 kilometers into the sky.
The engines are one of the most important components on this plane. It's like the heart. It doesn't beat, the body doesn't live.
Getting the A380 airborne would be impossible without the brilliant engineering innovators of the past. By the late 1800s, aviation pioneers recognized the need for power and thrust to obtain flight. In 1874, Frenchman Félix du Temple attached a steam engine to a monoplane.
Et voilà!
But the weight was all too much. In 1903, American professor Samuel Langley built a giant catapult to aid launch. But the takeoff didn't go as planned. Luckily, 2 siblings from Dayton, Ohio were about to make one of aviation's most significant breakthroughs. In December 1903, Wilbur and Orville Wright launched the maiden flight of the Wright Flyer. Two propellers driven by a piston engine gave the plane enough thrust to take to the air. Although only lasting 12 seconds, covering 36 meters, it was the first controlled powered flight and heralded the birth of modern aviation. However, more than a century on, getting a plane more than 1,500 times heavier than the Wright Flyer airborne would be impossible without a remarkable British innovator. Up until the late 1930s, piston engine propeller planes had been the aviation standard, but they were limited in range, speed and altitude. A radical solution was required.
What an incredible sensation!
Aerospace engineer Dr. Ben Evans is experiencing firsthand the power of the Gloucester Meteor, Britain's first ever jet fighter, and impossible without the genius of a British engineer. Frank Whittle, pioneer of the turbojet.
I can feel the acceleration pushing me back into my seat. And these 2 engines kick into work either side of the aircraft. You feeling okay? Yeah, good.
Whittle's new engines were powerful enough to carry the Gloucester Meteor vast distances at 12,000 meters high and at almost 1,000 kilometers per hour.
This was a leap forward in terms of the possibilities of what aircraft would be capable of doing.
As effective as it was, the concept behind the engineering was deceptively simple.
In essence, the way the jet engine works is you have suck, squeeze, bang, blow. You suck air in at the front here, and then that passes through a spinning compressor. And that compressor squeezes the air down, increases the pressure and the temperature of the air before it passes in to the combustion chamber. Now, this is the point where the fuel is added and ignited. This increases the temperature and the pressure of the gas even further. And then all of those hot exhaust gases have to expand, speed up through the back of the engine, and they pass through this turbine. And the turbine is connected via a shaft down the centre of the engine to the compressor at the front, making that spin. But what pushes the engine forward, what generates the thrust, is the expansion and the acceleration of the exhaust gases out of the nozzle at the back of the engine.
Whittle's turbojet allowed aircraft to fly faster, higher, and further, and changed the face of aviation forever.
So successful was Whittle's design that the jet engine has just become a standard now on modern commercial transport aircraft. The dream of travelling faster, higher, safely and more economical all over the world became a possibility.
To launch the A380, engineers would need to take Whittle's jet engine and augment its capabilities to an unprecedented level.
That size of aircraft couldn't exist before, though they had to develop and to design brand new engines to suit what's required to have it going upstairs in the air.
While it is serviced in the giant purpose-built hangar, technician Charlie Jackson has the chance for a detailed examination of the engines that power the monster plane.
The A380 has 4 huge engines, 70,000 pounds of thrust each, full of new technologies. It's one of the most advanced engines that's available on the market today.
These 4 specially developed mighty GP7200 turbofan jet engines are amongst the most powerful ever built. Each draws in enough air to inflate a hot air balloon every 3 seconds. And is nearly 50 times more powerful than Whittle's first turbojets. But in the modern world, its designers faced challenges that were about more than just power.
The main difficulty is to define an engine that is powerful, that gives economy to the airlines, and reduce noise.
Thanks to state-of-the-art design, the A380 burns 22% less fuel per seat than the average 747 jumbo.
These fan blades have been designed specially for this aircraft. They have a very revolutionary new shape to increase the airflow through the engine. 70% of the thrust from the engine actually comes from these blades, and not from the motor itself, which is burning the fuel and turning these blades.
Each of the 24 hollow titanium blades are boomerang-shaped, with a reversed sweep at the tip. This shape slows the air from supersonic to subsonic speeds, not only making the A380 more fuel-efficient per passenger than a family car, but also making it substantially quieter.
This aircraft is well below the limits of noise for the size of the aircraft. He's setting the standard.
But in creating this super jumbo, the team faced yet more challenges and would need to draw on history's engineering trailblazers.
If the whole airplane had been made from the traditional aluminum, it would have been catastrophic to the design.
To achieve more impossible engineering. The Airbus A380 is the biggest passenger airliner ever built. Capable of singular flights of nearly 16,000 kilometers, it is a triumph of aerospace engineering.
Getting an aircraft of this size off the ground to fly practically halfway around the world is an engineering feat.
The aircraft's huge range is mind-boggling, but it also provides designers with a challenge. The A380 would be capable of flying from Dallas to Sydney non-stop. And gigantic journeys require extra provisions for passenger comfort. Its 2 passenger decks provide a total area of 550 square meters, equivalent to 3 tennis courts. At a high-tech hangar in Paris, this Airbus is being stripped back as part of a scheduled service, revealing its engineering secrets.
It's quite impressive to fly on this aircraft. As you can see, it's a very long aircraft. In the business class, you have 80 seats. That's quite important.
But designing for comfort isn't new. In fact, one of aerospace's earliest and most successful innovators set the benchmark. The early aviators who took to the skies had little choice but to wrap up warm and brave the elements. But one man had other ideas. In 1913, brilliant Russian engineer Igor Sikorsky conceived the Ilya-Muromets, a plane engineered for luxury travel and the world's first airliner. By using a wind-driven generator and running pipes of hot air from the engine through the saloon, there was electricity and heating, a bedroom, toilet, and comfy seats. 16 passengers could travel up to 600 kilometers in style. With the onset of the First World War, after only 1 year in service, the aircraft was redesigned as a bomber. But the legacy of the Ilya-Muromets opened a new world of aviation possibilities. Capable of carrying hundreds of passengers in supreme comfort, over almost 16,000 kilometers, the A380 has redefined long-haul travel.
When you see at the aircraft outside, it's so big that when you come in, when you have a seat, you can imagine how loud it's gonna be when it's gonna take off. But in fact, no, it's quiet, and you don't even know you're in the air.
Transporting 500 plus passengers in comfort and safety is about more than just chilling champagne to the correct temperature. Flying at almost 1,000 kilometers per hour and nearly 4 kilometers high, with little more than a few centimeters between passengers and Mother Nature outside, posed the designers of the A380 a seemingly impossible challenge.
The forces that an airplane are subjected to on any flight are severe because it's having to expand, it's having to contract, it's having to deal with extreme temperatures. Even the aircraft is actually getting torsional effects on itself while it's flying through turbulent situations.
Since the 1920s, aluminium has been the material of choice for aircraft skins. It's flexible, strong, and light. But when you've set yourself the challenge of building the largest commercial airliner in the world, on which the paint alone weighs half a ton, every single gram counts.
If the whole airplane had been made from the traditional aluminum, it would have been catastrophic to the design. It would be way too heavy. They would have had to have bigger engines, they would have had to have bigger wings, it would have burned a heck of a lot more fuel, and it wouldn't fly very far.
Decreasing the weight by reducing the thickness of the aluminium skin simply wasn't an option, as engineer Ben Evans demonstrates in his lab at Swansea University.
So this gun is going to fire these baseballs at high speed at our target in the stand, and we'll find out how much damage they do.
The aluminium sheet is approximately half the thickness of a traditional aircraft skin.
Wow, let's have a look and see what's happened. And there's the damage. It's deformed this by a good 5 centimeters or so. So really quite a lot of damage with that impact on the aluminium sample.
The designers of the A380 needed a solution that was at least as strong as traditional aluminium, but lighter.
They needed to find materials that could create such a large aircraft that wouldn't weigh like a tank.
Solving this engineering conundrum would be impossible without the great innovators of the past. In the 1930s, American engineer Virginius E. Clark created a brand new alternative to aluminium. Birchboard was impregnated with phenolic resin and laminated under extreme heat. The resulting material he called Duramold. Used in Howard Hughes' famously enormous Spruce Goose seaplane, it was one of the earliest and most successful examples of an aviation composite.
Composites are made up of more than one material and take advantage of the best of both worlds. What we're going to do to prove this is the case is impact test a composite.
This composite is a woven carbon fibre impregnated with epoxy resin, the same dimensions as the thin aluminium Ben tested earlier.
Woo! Literally nothing. So that impacted right here, bang in the middle. In fact, there is absolutely no sign that any damage has been done. So these are the results. This is the composite, this is the aluminium, the same impact force, but look at the damage on the aluminium. So that is a result for the composite. A lighter material and a stronger material. And that is why this stuff is being used by aerospace engineers today.
To build the world's largest passenger plane, engineers would take Virginius Clark's innovations with composites to the next level and create a brand new material for the A380. Made up of thinner than usual aluminium reinforced with glass fibre, they called it Glare.
The composite materials that make up this aircraft, they're as strong as the traditional materials, and they're as flexible as the traditional materials as well. To give an example of how sturdy they are, there's more than 1 ton of air pushed inside this aircraft when it's flying, when it's pressurized.
Using composites saved 15 tons on the overall weight, making this seemingly impossible aircraft possible.
If they hadn't used Glare or a similar composite, the aircraft that we have today probably wouldn't exist.
It's not just the materials on the A380 that make it stand out from the crowd. Even the method of construction breaks the mold. Sections are built in factories in France, Germany, the UK and Spain before being transported to Toulouse for assembly. The transportation alone required specially commissioned ships and the use of Airbus's improbable-looking A300-600 ST or Beluga super transporter plane. Each A380 contains 4 million individual components, which, once assembled, create an airliner of record-breaking proportions.
I guess this aircraft makes everybody dream when you see it. When people are waiting to go inside the aircraft, you can see children looking at it. People are really excited.
But to make this monster machine flyable, its designers would yet again have to turn to the great innovators of the past.
Often in engineering, the simple solutions are the best solutions.
To produce even more impossible engineering. The Airbus A380 is one of the most technologically advanced commercial airliners in the world.
The technologies used in the design of this machine were not existing 20 years ago.
But for its designers, redefining the terms of modern aviation would mean overcoming some seemingly impossible engineering conundrums.
They told everybody in the world that they will build the biggest aircraft in the world, so it was quite a challenge for them.
And one of the biggest challenges directly relates to the plane's size. Calculations revealed that the ideal, most efficient wingspan for this massive aircraft would be 82.5 meters. But aviation rules state that all planes should be able to fit into an 80-meter box. If the wingspan couldn't be reduced, the A380 would be incompatible with all the world's airports. The answer would lie in one of the great aircraft innovations of the 1970s. In 1973, the world was entering an oil crisis. An embargo on sales to the West saw prices quadruple overnight. And the aviation industry was paying the price. As Dr. Ben Evans demonstrates, traditional wing design has its drawbacks.
Aerodynamicists are always trying to improve the efficiency of wings, which really means trying to improve the ratio of the lift to the drag of the wing. One of the things that was causing a lot of drag and dropping the lift on the wing was what's called a wingtip vortex.
The wind tunnel is simulating an ordinary wing traveling through the air at a typical cruising speed.
In the central section of the wing, you can see that the smoke is very smooth until it reaches the tip of the wing. And once we're at the tip of the wing, you can see this vortex pattern forming.
A wingtip vortex is caused when high-pressure air under the wing spills upwards at the tip to meet low-pressure air above. This creates turbulence and therefore drag, forcing the engine to work harder. The 1970s fuel crisis meant a solution was needed, and aeronautical engineer Richard Whitcomb, working on NASA's Aircraft Energy Efficiency Program, found one. Whitcomb suggested that by changing the design of an aircraft's wingtips into vertical winglets, they would create less drag and burn less fuel.
As I move the smoke trace towards the end of the wing this time, instead of having the single strong vortex that we saw in the case without the winglets, what's happening now is that the flow is smearing out almost into a sheet, making the wing more efficient.
Adding a winglet prevents the mixing of the two airflows above and below the wing, reducing the vortex. The A380 has specially designed arrow-shaped winglets called wingtip fences. And they allow the wingspan to be reduced to just under the maximum 80 meters without compromising the aircraft's efficiency.
Without those design features, this aircraft would be way too big, it wouldn't be practical, and it wouldn't exist today.
Despite its aerodynamic efficiencies, the A380 is still enormous. So how could its creators make it possible for pilots to control this mighty beast, which, fully laden with fuel and passengers, weighs a staggering 560 tons? Once upon a time, it would have been an impossible dream. By the 1960s, the age of the jet was in full swing. Transcontinental travel had never been easier or faster. But a group of audacious Anglo-French engineers thought it was possible to go even faster. To create a supersonic passenger jet.
There were a lot of engineers who said, well, this isn't possible. What you're proposing here is just too ambitious. The result of the work of those pioneering engineers is this, Concorde.
Launched in 1969, Concorde could reach speeds of over 2,000 kilometers per hour. More than twice the speed of sound. Flight times between New York and London were cut in half. But flying this futuristic jet airliner would be virtually impossible using traditional aircraft controls. Concorde would need an innovative new system known as fly-by-wire. At a simulator at Brooklands Air Museum, former Chief Concorde pilot Mike Bannister explains.
You could fly at 1,350 miles an hour, faster than a rifle bullet. Concorde wouldn't have been possible without fly-by-wire because some of the control forces at certain flight conditions really would have been huge.
What exactly is fly-by-wire?
Fly-by-wire is computers telling systems what I want to do. On a conventional airplane, when I want to turn left, I do that, and some pulleys and wheels and cables move the controls. On this airplane, when I want to turn, I do that. It tells a computer that tells the controls what to do. That means the airplane's far more responsive, it can be far more efficient, and is capable of being flown by ordinary human beings.
Concorde was the first commercial jet to adopt the technology.
What did it feel like to fly the real Concorde?
The airplane's a delight to fly. It's like a thoroughbred racehorse rather than a riding school hack, or a sports car rather than a truck. It is so responsive. You can fly it with your fingertips, so why don't you have a go? Very nice. Keep it coming, that's perfect. Right through the bridge. London Assembly Building to the left, a Shard to the left. Fabulous.
Well, Concorde clearly is a remarkable aircraft. Not only is its exterior breathtakingly beautiful, but underneath the skin there is some technology that really revolutionised the aviation landscape and has made what we can do with modern aircraft today possible.
Since its first application on a commercial airliner, fly-by-wire systems have become industry standard. And on board the A380, a highly sophisticated digital system makes flying this super jumbo possible.
For an aircraft the size of this aircraft, it is relatively a simple aircraft to operate. For flying, the aircraft is here, and it is completely electronic. I mean, there's no cables. It's all generating electrical inputs, which are sent to a computer, which then send the signal onto the flight control surfaces to move.
Spanning some 13 years, the design and development of the Airbus A380 ranks as one of the aviation industry's greatest achievements. Now the A380 is operated by airlines across the globe, and one takes off and lands every 4 minutes. By drawing on the innovations of the past, adapting, improving them, and making groundbreaking innovations of their own. Aerospace engineers overcame extraordinary obstacles and succeeded in making the impossible possible.
It was quite difficult to imagine 20 years ago that kind of machine you have here was going to exist, but it's now reality. So what about the future? Who knows? Maybe going to the space with an aircraft.